Labas rytas.
Labą rytą.
Labą Dear participants, key speakers, listeners, and guests, I'm Eimantas Nenishkis, a chief organizer of the CYSENI conference. On behalf of the whole organizing committee, I would like to welcome you to the 17th International Conference of Young Scientists on Energy and Natural Science Issues. Unfortunately, last year, due to the sudden outbreak of coronavirus pandemic, we had to cancel the event. However, we did not waste our time and spent in expanding and preparing for hosting this year's conference online. During initial discussions on this year's conference within the organizing committee, we decided it will be hosted fully online. That was a hard decision, as we would really prefer to see you all in person in Kaunas. However, safety first. Nevertheless, we put a lot of thought and effort into providing the best online conference experience. Through RTO Lithuania, an association of non-university research and technology organizations, we, the Lithuanian Energy Institute, the Lithuanian Research Center for Agriculture and Forestry, as well as the Center for Physics Sciences and Technology, established a partnership in co-organizing the CYSENI conference. This partnership allowed us to expand the topics from mostly energy-related issues to 20 topics in 3 sections: energy, physical, and environmental sciences. Some of you who participate in CYSENI conference not for the first time might have noticed apologize for a small technical issue. So this year we started a partnership with RTO Lithuania, an association of non-university research and technology organizations. And we, Lithuanian Energy Institute, the Lithuanian Research Center for Agriculture and Forestry, as well as Center for Physical Sciences and Technology, established a partnership in organizing the CYSENI conference. And this partnership allowed us to expand the topics from mostly energy-related issues to 20 topics in 3 sections: energy, physical, and environmental sciences. Some of you who participate in the CYSENI conference, not for the first time, might have noticed that we made a slight change in the conference title. It's no longer a conference just on energy issues, but now on energy and natural science issues. It seems that the new title even fits the acronym better. This year, we also started a partnership with 2 open access MDPI journals. The first one is Energies, and the second one is Plants, which we hope will be an excellent platform and opportunity for the best papers of the conference to be published and shared with the scientific community worldwide. It seems all of our work has really paid off, because this year we have a record high number of presentations, 177 by 173 participants from 29 countries. Since we have participants from all around the world to avoid connection problems and ensure the best watching experience, the decision was made to upload recorded presentations instead of having live ones. You will find all presentations by our participants accessible through the CYSENI's website for participants section. It will require a password, but if you do not have one, do not worry, as you can quickly get it by filling a small form. There is a visitor registration selection under the For Participants section. In addition to recorded presentations by the participants, we will have 7 live presentations by our key speakers today. More about that just a bit later. We hope you will find the event interesting and informative. And now, I would like to ask a director of Lithuanian Energy Institute, Sigitas Rinkevičius, to give a word of welcome.
Dear guests, participants of your conference and colleagues, do you hear me well?
Yes, we can hear you loud and clearly.
Thank you. I welcome you all in our already 70th International Conference of Young Scientists, CYSENI. As already mentioned by Chief Organizer of your conference, Mr. Eimantas Neniškis, after 16 CYSENI conferences organized by the Lithuanian Energy Institute, this year we established a partnership with other institutes for co-organizing this conference, expanding the list of topics. Similarly, as in previous conferences, all topics of this conference will contribute to worldwide objectives in fighting with climate change. The European Union countries have especially ambitious goals in this respect. So-called the European Green Deal is initiated with a clear vision to achieve climate neutrality in Europe by 2050. My expectation is that a broader list of our conference will provide better opportunities to address this challenge, because this challenge requires multidisciplinary solutions and covers not just energy field, but also agriculture, transport, municipalities, and other sectors. Social sciences are also important and will be addressed in the conference as one of the horizontal topics important for Green Deal, because any technological solutions require public acceptance and economic justification in order to be successfully implemented in the real world. Mobilizing research and fostering innovation is indicated as one of key elements of the European Green Deal, and major European Union research and innovation program Horizon Europe will play important role in solving climate and environmental related challenges. The CYSENI conference is a good place to discuss related research topics, to initiate and strengthen international cooperation. I hope that after this conference, the young scientists will contribute, proposing new ideas and implementing new international projects in the frames of Horizon Europe and other international programs, as well as in the frames of different bilateral programs. Talking about the Lithuanian Energy Institute, I would like to point that our institute is very much interested and oriented to the international cooperation. The Lithuanian Energy Institute is currently the third institution in Lithuania by number and funding of Horizon 2020 projects, and was or is involved in 26 projects of this program in different energy research topics. 3 of these Horizon 2020 projects are under coordination of Lithuanian Energy Institute. Despite this success, we have ambition to increase our participation even more in new European Union research and innovations program Horizon Europe, and we see the importance of pilot and demonstration projects in order to achieve this. We developed at our institute the vision of research and development and innovations infrastructure for integrated smart energy systems in the campus of Lithuanian Energy Institute, which would be used as the model of the smart city. The vision includes the technologies of generation and multifunctional use of hydrogen, which is seen as key component in the implementation of Green Deal objectives. The realization of this vision we see as a way for implement and more active participation of business and research partners in international large-scale research and development demo projects, and we expect understanding and support for this idea implementation from the Lithuanian ministries and our beneficiaries. We at the Lithuanian Energy Institute continuously look to new projects. Currently, we work on a number of new proposals for projects in different topics of energy research. The researchers of the Lithuanian Energy Institute work in fundamental and applied energy-related research areas in many topics, from renewable energy, mainly bioenergy, till the nuclear, including energy storage, including hydrogen technologies, smart energy grids, energy economy, hydrology, and material research. All these topics are addressed in the CYSENI conference, so all participants of the conference will be able to know more about our activities in the papers and presentations submitted for this conference. I would like to use this opportunity to inform you, especially young scientists, that we in Lithuanian Energy Institute have PhD studies in energy research and invite young researchers from Lithuania and abroad to apply for their PhD studies in Lithuanian Energy Institute. Applications for 2021 two PhD studies at our institute will be open shortly in the beginning of June, with deadline for submission of applications by 22nd of June. The information about application process is available in the Lithuanian Energy Institute website. Dear young scientists, you are our future, our guarantee of continuity of research activities which are so important for future of our planet and its citizens. Please enjoy this conference, make new international contacts, and hopefully we will have possibility to arrange next 18 CYSENI conference, not virtually already, but live here in Kaunas. Thank you for your attention.
Thank you, Director. And now we introduce our audience to Mr. Arminas Varanauskas, Director of RTO Lithuania, an umbrella organization for which the three institutes formed a partnership that further translated in organizing this event. The partnership gave root to new ideas and additional resources which were necessary to expand and improve the quality of the conference. Mr. Arminas, the floor is yours.
Thank you very much, Eimantas. After such a wonderful introduction, there is not a lot of left to add, but I really want to congratulate all the participants who able to attend this event, even though it is taking place virtually, but this is our current reality, and we all need to find the better ways how we can work with it. We as our RTO Lithuania are very happy that this is our partnership project which we have among all our institutions, namely Lithuanian Research Center for Agriculture and Forestry, Center for Physical Sciences and Technology, and of course initiative coordinator and father of this initiative, probably the right thing to say, Lithuanian Energy Institute. We as an RTO Lithuania encourage further cooperation among these institutes through internal funding program which aimed at financing joint projects on Green Deal topics, as previously mentioned as well. And also we are actively participating in science and innovation policy making, both nationally and internationally. We're working directly with our Lina office and trying to participate in many different activities which are happening in Europe as well. So I just this morning finished one book or a course, so to say, by the Lithuanian descendant who is currently now working at a Knoxville University in Tennessee, Vėjas Gabriel Lulevičius, and the book is about the history's great voyages of exploration. And that book teach me two things. I think they are precisely good for this conference. And I also encourage to read everyone that book who are keen on Fernweh, which is for English from the German would be a longing for far-off places, which science gives us as well. So two things. One thing is that more complex explorations and voyages was done not by single people, but by cooperation. And this is what RTO LT and this conference is built on. And the second one is that one voyages leads to another voyages. So I really, really invite you to use this conference as a bridging bridge to strengthen your cooperation and have new ideas in place after that. Thank you and have a good conference.
Mr. Arvenes, once again, we are very grateful for the contribution of RTO in improving the CYSENI conference. Now we will move to our guests. We have invited guests from the ministries as well as Kaunas municipality. We, the researchers, often see the impacts and the importance of our work on a very narrow scope, while policymakers have a much broader view. We are the ones who see how studies translate to the real world impacts. We believe that close collaboration between policymakers and scientific community is essential, especially now when we have such ambitious national and international sustainability goals. Now, when the world is dealing with coronavirus pandemic, please welcome the first guest, the Vice Minister of Education, Science and Sport, Mr. Gintautas Jakštas.
Good morning, dear hosts and participants. I'm glad to be at this conference and welcome you all on behalf of the Ministry of Education, Science and Sport. Being organized already for the 17th time, this annual event confirms its relevance and the need of the energy, physical and environmental sciences, both in our country and internationally. Our gratitude is dedicated to the organizers for their enthusiasm and efforts to go forward. Lithuania seeks to be active and visible in European research and innovation landscape, as well as in the global context. For this, a combination of modern infrastructure and high competence researchers is essential for us. In Lithuania, we plan to consolidate scientific potential in priority areas of smart specialization by development of innovation ecosystems and creation of centers of excellence. Those centers will serve as a platform for cooperation between different research institutions and businesses. A critical mass of talented research and professionals is a key for our progress. Therefore, we aim to become a center of talents attraction. Our government plans to double funding for research and innovation, to improve conditions for researchers' career, and to support open science activities. We strongly believe that these actions will further foster favorable conditions for seeking the leadership in Green Deal research and innovation activities in which the Lithuanian higher education and research institutions have a great potential. It should also serve for higher interdisciplinarity and more intensive interinstitutional cooperation. This conference is an excellent opportunity to present research works and results, to establish new links and develop the existing ones. Therefore, I would like to wish the very best success to all participants in achieving these goals. Thank you very much.
Thank you, Vice Minister Mr. Gintautas Jakštas. Globally, the most greenhouse gas emitting sector is the energy sector. Therefore, rapid and radical changes are necessary to mitigate the climate change. Complex solutions are needed not only at the supply side, but at transmission and distribution side as well. What makes this task so complicated is that we have to make energy supply not just sustainable, but also cheap, safe, and reliable. Our second guest is a representative of Energy Ministry of the Republic of Lithuania, Mr. Žilvinas Danys.
Sorry, but we have a Vice Minister, Albinas Zananavičius, so good morning to everyone, but the floor is for Albinas Zananavičius, Vice Minister of Ministry of Energy.
Yes, good morning, everyone, and I would like also on behalf of the Ministry of Energy to congratulate and thank you all for connecting to this meeting. I think in more normal times we would probably have met physically in Vilnius. Some of you would have traveled long distances to meet each other and to share your ideas. I think this will have to be postponed for better times, but today it is obvious that energy sector is entering into a crucial stage of transformation. We can no longer exist and live in the same situation as we used to be. So therefore, energy will be one of the sectors where transformation will be needed. It is quite obvious that we have already an agreement in the European Union on how we will be living in the future, that we cannot postpone our environmental and climate objectives to future generations. Therefore, decisions need to be taken now. The biggest challenges that we are facing, and we are dealing with them already now, is inclusion and integration of renewable energy into the traditional electricity grids, for example. We also have enormous challenges in the energy efficiency, where additional efforts are needed and bright ideas are needed also. At the same time, we have to ensure that during this energy transformation, our energy supplies remain competitive and they remain reliable. And therefore, I think science here is of the utmost importance, and we will need all the ideas, bright ideas from young researchers in order to do that transformation in the most efficient and most planet-friendly way. Lithuania has a new government, and the government's program has also included several very important features as far as renewable energy is concerned. I think one of the most promising areas where we are extremely interested in the research and innovation is hydrogen. We have already created our national platform. We will be allocating 20 million euros for innovative hydrogen projects. We will also do digital transformation of our energy sector, and all the future generation in Lithuania will come from renewable energy. I think this conference is an immense opportunity to share ideas and to contribute in the practical ways to achieving goals of Lithuania's energy transformation, and also to achieve goals of European and global energy transformation. Therefore, I wish a successful conference to all of you. And what is most important, I wish that all your dreams and all your ideas would be implemented and contribute to the progress of humanity. Thank you very much.
Vice Minister, Mr. Albinas Zananavičius, thank you for your word of welcome, and I really apologize for the error in the introduction. Usually, CYSENI conference takes place in a wonderful city of Kaunas, which is nicknamed as student capital. Kaunas has almost 300,000 inhabitants, but houses 4 universities, 4 colleges, and 7 vocational schools. Around 14% of inhabitants are students. The last guest is Mr. Raimondas Endrikis, a representative of Kaunas municipality. Mr. Raimondas, the screen is yours.
Hello, everyone. Dear organizers and participants of the conference, it is a great honor to say words of greetings to you at this event. The theme of the conference has been of particular importance recently. Energy and natural sciences issues have for some time become a special challenge for Lithuania, Europe, and the rest of the world due to scarce resources, especially due to the impact of the environment and changing climate. Kaunas is a green city. This fact means not only that here we have one of the most famous European basketball club, Žalgiris, with the dominant green color. The course chosen by Kaunas for the future of our growing city is also green. Renewable energy sources, creation of a sustainable city, sustainability with the environment are frequent themes and decisive factors in making today's decision in Kaunas. The projects currently being implemented in Kaunas are focused on ecology, sustainability, and social relations. In this way, we seek to become the center for innovation where it is convenient to live and work. Last year, we introduced a sustainable mobility plan for which we received a remarkable assessment from the European Commission. We want to make urban schools autonomous by installing solar power plants on the roofs of all establishments. 2 years ago, the main heat supplier of the city, Kauno Energia, received an award modernization of Kauna's heat sector, which had the greatest positive on efficiency and reduction of carbon dioxide emissions. Another today's project is also worth mentioning. It is Aleksotas Innovation Industrial Park. The former military industry territory is being converted into a high-tech and innovation valley. Next year, in the very center of Kaunas, the Museum of Science, Isle of Science, will open its doors. It will encourage even the youngest residents and guests of the city to take interest in scientific achievements and sustainable development. Moreover, it is worth noting that Kaunas is one of the most academic cities in Lithuania, where engineers of the highest level as well as scientists are prepared. Therefore, such events are particularly welcome because they provide opportunities for professionals who are shaping our future to present their achievements, share their insights and visions. So all of these factors show that the topics you are working on today are particularly relevant to our city. Therefore, as a representative of Kaunas City Municipality, I wish you an informative and meaningful conference as well as good insights for each of you. Finally, I invite all foreign guests to visit European Capital of Culture 2022 next year. Thank you for inviting and have a great event.
Thank you, Mr. Raimondas Hendrikis. And once again, big thanks to all our guests. Now we will be having presentations by the key speakers. On behalf of organizing committee, I would like to express my additional acknowledgement for them because we are very grateful that 7 internationally recognized experts agreed to share their insights and experience with new generation of young researchers. Today, we will hear presentations from Dr. Bogdan Voisev from Dresden University of Technology on direct laser interference patterning, Dr. Erik Kjellström, a professor at Swedish Meteorological and Hydrological Institute, about climate modeling in support of adapting the energy sector for future climate conditions in Northern Europe, Dr. Ana Luisa Fernando, an associate professor in Nova University Lisbon, on the cultivation of energy crops in marginal soils, technological, environmental, social, and economic opportunities and risks, Dr. Zigmas Balavičius, the head of the Plasmonics and Nanophotonics Laboratory at Center of Physical Sciences and Technology. He will give a presentation on plasmonics from biosensing to nanolasers. Dr. Tom Lindros, a senior scientist at VTT, Technical Research Center of Finland. He will talk about decarbonization and electrification in Baltic countries and Northern Europe. Dr. Roman Antipenko, a deputy head of the Allegra Laser Development Group at ELI Beamlines. He will present advanced laser systems at ELI Beamlines facility from 3 terawatts to 10 petawatts. And the last but not least presentation will be by Paula Pero Garcia, an executive coordinator of Horizon 2020 Auroral Project. This presentation will be about smarter communities, a new paradigm for Europe. After first 3 presentations, we will have 1 hour lunch break. We will continue 12:30 in Central European time or 1:30 in Eastern European time. You will have an opportunity to give questions to the key speakers using YouTube live chat. If you don't see it, it is likely that you're watching the live stream through CYSENI's website or the Facebook page. Just open it on YouTube. After each presentation, if there will be any time left, we will ask the presenter selected questions. You can leave a question anytime during the presentation, as well as a person tracking all the comments. A quick note, only questions relevant to the presentation's topic will be selected. We will conclude the live session at 3 p.m. Central European Time or 4 p.m. Eastern European Time. There will be no further live sessions. However, 177 presentations by the conference participants will be available for watching on CYSENI's website during the conference days. To access them, go to CYSENI.com for participant section on conference access. It will require a password. If you do not have one, please fill a small registration form in visitor registration under for participants section and you will immediately receive it. Once you access the participant section, you will see a menu bar with 3 conference sections: energy, physical, and environmental sciences. Select the one you're interested in. The list of conference topics will update. If you will click on the topic, it will expand and all presentations assigned to this topic will be visible to you. If you want to leave a comment or a question to the authors, there is a comment box for that below the video. Comments are manually moderated, so it might take some time before they become visible to everybody. Papers and extended abstracts by the participants will be published in the conference proceedings, which will be prepared and uploaded to the CYSENI's website by June 13. So now we'll have a small 8-minute break and we'll continue 20 to 11 in Eastern European Time and 20 to 10 in Central European Time. We'll be back shortly. Let me introduce you the first speaker, Dr. Bogdan Wojcik, a senior research scientist in the Technical University of Dresden, one of the largest technical universities in Germany, an expert in the field of laser material processing. He has more than 70 scientific publications and 6 patents. Today, he will introduce you with the direct laser interference patterning technology, key features, and the most interesting application. Please welcome Dr. Wojcik.
Hello, I hear some voices still. Is that normal?
You should not probably, you should mute the YouTube live stream if you open it.
Yeah, that's true. That's sorry. Yeah, so thank you, Mr. Chairman, for introduction, and also for the conference organizers for inviting me. It's really a big pleasure to being able to introduce you to this technology in this maybe not directly related topic to this technology. I will maybe start from the first slide. I have to share my screen.
Please press
Yes.
share screen, the green button.
Yes, that's right. It just was disappeared. Okay, now it should be fine. Yeah, do you see?
Yes, we can see it clearly.
Okay, so, and I will talk today about the direct laser interference patterning. And yeah, it's not really directly related with the topic of the energetic topics and applications, but it definitely can be used in this field, and those listeners who are listening to this topic, maybe it will give you some ideas where we can collaborate and use this technique in the field of energy. So I come from Dresden, University of Dresden, which is one of the capital city of the state Saxony. And even though I come from Technical University of Dresden, we also work very closely together with Fraunhofer IWS. It's a huge institute in Germany. And we all collaborate in the frame of CAMP Center, or like Center of Advanced and Microphotonics, where we work very strongly on the topics related to the surface patterning in order to provide some functions to the surface of material. And we also not only make our work on the scientific questions, but also we try to create the products that can be sold commercially and so on. And why we are interested in that? It's because in today's global market, companies have to compete, and in order to do that, they have to improve their products, and often they do it through the surface structuring, or the in order to provide some functions to the surface. And these ideas are coming from nature. The nature itself is doing such things. For example, like rice leaves, which has such an ability to prevent wetting, or like water on those leaves rolls out, and this is super hydrophobic surfaces, which can even be used in the energetic topics. For example, in solar cells, in order to keep the surfaces of the solar cells clean after rain, and any dust or residual materials that can be on the surface can be to keep it clean from that. Can be used, for example, shark skin is very friction reduction skin that reduces the friction with the water, so that the shark can swim better and more efficient. So that also can be used in energetic fields, for example, in windmills, in order to reduce the rotation friction of the windmills. Also can be used for decorative areas. For example, like butterflies, they have their wings in color, and that's not because they have some kind of paint on the wings. Of course, it's because of the structure which is inside inside the wings. And you can see it's a very tiny structure, less than 1 micrometers, which can shape the light so that only a certain color is reflected, and you see a blue color. And therefore, it can be we are aiming to take that capabilities of nature and transfer to the industry or to the real world. So how we can do it? Here in TU Dresden, by direct laser brighting or laser marking can be also used. It's a technique that uses laser light, very powerful laser light that focuses into the surface, and with this you can directly remove the surface or ablate it. So you can like mark on the surface, or for example here you can see how fast it can work. It can be used with the scanner system, can be used on many different materials, also with different shapes of materials. And it also can be used to make a 2D structures by engraving the surface. So why then direct laser interference patterning? Well, first of all, if you look to the main way how that technology works, as I already told you, it focuses the strong laser beam into tiny spot, bringing huge amount of energy into the small spot. By scanning the sample or the surface, what you want to structure, you can ablate certain patterns on it, directly remove the material and form certain patterns. The problem with this technique that it's usually not very good in terms of high resolution. The resolution is limited to 10 micron, which is still small if you think, because the human here is 100 micron, but still not enough for those structures that I already mentioned, because they are even more tiny. And also this technique is not fast enough for this kind of purpose, because as you saw before, in order to make the pattern, you have to make it pixel by pixel. So the smaller the pattern, the more time is needed to structure, as you can see in this graph here. The smaller the structure, the time decreases quadratically. Therefore, it's not efficient. But when we use direct laser interference patterning, which is very simple technique, but instead of one beam, we split the laser beams into 2, 4, or even 6. And with this, we split also the intensity of the laser beam at the sample surface in many small spots. What that gives to us is that the ability to structure way tinier structures with the same optics, with let's say the same costs. And therefore we can go down to 400 nanometers. And another benefit from this, as you can see here, with single shot, we can structure the whole structure with just a single shot in that area, which gives us also efficiency in making such structures on the surface, because it does not depend on the feature sizes. And therefore, the smaller the feature sizes, the more efficient this technique is. Okay. And yeah, just very short introduction about this method, so that you know how it works and you know the capabilities of this technique. So as I said, it's basically what it's doing is just putting many laser beams into single area where they interfere. And as you can see, it's not that you can get only many intensity peaks. You can also form lines and other structures, and also change the distribution of these intensity peaks by just changing the number of beams. And that can be accomplished quite easy. But that's not only the limit. There are also other properties of the light that you can adjust. There is a phase of the beams that you can also adjust, and gives you even more capabilities to get different kind of structures. And there is also a polarization of the light that you also can adjust and create even more different kind of structures, like you see here. And you saw before that this is quite important. At the beginning of my talk, I told that it is quite important to have many of these kind of structures, because you saw that different functionalities that appear on the surface by nature, they also depend on the structure of the surface. Therefore, it's important to be able to make different kind of structuring shapes. So how to make laser interference? You can think that it's not so easy. Like you need a huge amount of optics, a lot of experience, and so on, and a lot of money to build this kind of setups. But it's not really true, because in this case it's a very simple technique. For example, here in TU Dresden, we built a very simple optical setup for this purpose, which is made of diffractive optical element. This is the element that splits the beam into 1 or 2 or 4 or even 6 beams. And then we just use a prism, glass prism, to collect them and parallelize. And then we put a lens in order to focus them on the single spot. So you can see it's just a free optical element. And what is nice that by moving the prism, you can even change the period of the structure. Therefore, you have even more flexibility, and you can control that structure period very, very accurately. And we together with Fraunhofer IWS, we already built special, like commercially available machines for that, or the heads, which can do this application, this interference of the beams. You can buy it commercially. And yeah, of course, this technology therefore is patented. And how looks the basic machine that is doing this kind of structuring? It's very also quite simple and does not require clean rooms or something. Therefore, it can be used easily in the industrial environment. So it's based on the laser, of course. Can be different kind of lasers. Usually should be pulsed lasers, and then the head, which is I already introduced you in the beginning. Of course, should under the head is placed the material or the surface or the sample that has to be structured, and there should be some positioning machines that position that sample in respect to the laser beams. And this is one of the examples that we have in our lab for this kind of patterning. It looks very simple and easy to build. So what can be done with this technique? So by scanning the beam, as you see in this manner, or distributing the spots in this manner around, across the surface, we can make different kinds of structures. And only by 2 and 4 beam interference, we can produce these kind of structures, which can be just periodically distributed craters, lines. We can combine some different structuring to create hierarchical structures, which are combined from bigger features on top of, and having on top smaller features. And yeah, we can also build pillars that you will see later can be useful for hydrophobic surface formation. And also these kind of structures can be done on various kinds of materials, like polymers, coatings, oxides, even glasses, and so on. So where these kind of structures can be used, why we do them, why we should form them. I told you before that in nature there are some examples, but do we reach any of them, for example, so that we can show that this technique can be used to mimic those nature behavior? So one of the application could be for decoration. You can see already in industry there are a huge amount of products that has these colorful features on top, which is based on diffraction gratings. These are just periodical structures on the surface, can be just, as you see here, like a craters distributed periodically. And what it does, it just diffracts the white light that is coming to the surface into the colors. That's why you see these color rainbow effect on such kind of structures. And if you combine different sizes of those structures into the single area, you can create images. And this is an example of one of those applications made on the steel surface in our lab. With the technology that I already introduced. You can see that you can create really nice and colorful images directly on the steel surface without any additional post-processing of that, or of the surface. And it can be used for huge areas. In this case, you see it's 200 millimeter in white, but can be even in bigger and so on, so can be used in industry. But as you can see here, it's a little bit the issue that you don't see the color everywhere the same. Like here, for example, these letters, if you want to be them with the same color, usually you can't do that because you see this rainbow effect. So it's like holographical effect that some people, some companies want to have, but sometimes you need the real colors, and that is because when you look into that structure, you see it at different angles, and the color that comes to you also is different because of that different angle. So therefore, if you try to make areas of the same size structure, you have color at the top, but the color is changing along the structure. That is not good if you want to make nice colors. But what if you change the period of the structure across the whole structured area? So in this case, you can shift one of those diffractive angles and make the colors appear the same. And therefore you can homogenize this color, which is something new that we have created with this DLIP technology. And it brings the capability to make real pictures without any paint, and you see real colors. As you can see here, for example, it's Bart Simpson with the real colors like red, blue, and yellow, and we can even here you can see even more colors. And this is not that painting, you see it just because the light reflects from that surface. And we can even create white light, which is not really typical in the rainbow. You cannot see white light. By combining the colors, we can make a white light. And this is being able only because our technique is flexible in terms of changing the period of the structure during the processing. That is unique. So what else can we do with direct laser interference patterning? And one of the other fields that we focused is superhydrophobic surfaces. And these kind of surfaces are they repel the water from the surface. So for example, here you can see one of the ways how to measure that. Usually what people do, they just apply a small droplet on the water surface, and then they look how this droplet behaves, or how it looks on the surface. And there are three types of surfaces that can be distinguished. One is hydrophilic, when the water droplet really wets the surface, and you see it spreads and becomes sticked into the surface. And but some surfaces behave not so strongly like that, and they adhere the water not so strongly, and you can measure that by the contact angle from here, as you see here. So these kind of surfaces are hydrophobic, where the contact angle is more than 90 degrees. And there are also super hydrophobic surfaces with the contact angle more than 160 degrees. And this kind of surface behaves by repelling the water itself. They do not like the water, which is nice for keeping the surface clean. So for example, here is it's a 3D image of the pattern that we created with the direct laser interference patterning. And you can see that these kind of surfaces really behaves as superhydrophobic surfaces. This is a droplet placed on that kind of patterned surface. And this is the reference droplet. You see it really stick to the surface. And here you can see some snapshots of the droplet that is dropped from some distance from such a surface, and it starts to bounce. which is a nice result for that. It really shows that surface does not like the water to be on it, so it repels it. And here is a video made where we also have this patterned structure, and when the droplet comes from top, you see it just bounce away. So this structure really is not wetting, and therefore it stays clean. And even though if you place this kind of structure into the water and try to pour that water on top of that kind of structure, it's not possible. The structure just tries to repel it. And there is no chemistry on top, nothing, just a laser structuring. Okay, so another application, which is also quite close to the industry, for example, because it's improvement of biocompatibility of dental implants. And what we do here, we try to increase the adhesion of biocells from the bone, which is so that they can grow more. Let's say the environment or the surface is more friendly to those cells, and it is known that any rough surface, it's more attractive for cells to grow, and it's a common technique to make those dental implants being friendly to the human body is just by roughening the surface, and it is done by, and it is usually done by sandblasting, then some chemical etching and anodization. This is quite long time process. It's 1.4 minutes is required for a single dental implant to being able to structure. And there are also some problems like contaminations. There are still left some sand pieces in that dental implant that can cause some problems. And also there is some waste chemicals that are used for this process. Therefore, what we did, we structured these kind of implants with direct laser interference patterning by using 2 laser beams. We created the structure of line likes on top, and we the process of creation of this line structure was much shorter. It's just 6 seconds, and we calculated the price, which is only 13 cents, even less than a cent for the single implant. So, and when we measured how the cells grow on these kind of sources, we saw that the growth is way better on the direct laser interference patterning surface. The cells like to grow on this kind of surface even better. So that's reduces the problems related with the implant fixation in the human body. And also, as you saw, so there are 2 things: it's cells grows better, and also it's faster process. So it's also coming quite close to the industrial applications. And related to the hydrophobic surfaces that I already showed you, we can also these kind of surfaces can be much more easier to clean because of this hydrophobicity. For example, here you see the surface, which is also direct laser interference patterned, and it can repel, or it can clean the contamination on top of it is a dust particles here. You can see how easily you can clean that. If you look into slow motion movie, it's you can see that this droplet is not connected to the surface, not sticking to the surface, and therefore it rolls off that surface, collecting those dust particles. And that's how the cleaning process appears, because those dust particles become wetted by the surface and brought away. I couldn't even stand and put also a nice scene from the movie where a similar situation is happening. So can we come to the industry even closer and with this technique? And I want to show you some examples where we are trying to and almost get to the industrial application where this technology is really used in, can be used in industry. And one of that is, again, related to the hydrophobic surfaces. We created these pillar-like structures that are structured on the metal sheets, which are later placed on the front face of the Airbus plane. And we are now, these kind of planes are now flying, and there are different also other types of structures together placed for testing, and these kind of planes are now flying, and these structures are being tested in order to find out if the snow that is sticking into the surface can be repelled, is not sticking so that in the reference planes. This is a problem because, you know, especially in winter, those planes, you can see before the flight how staff are coming and applying some chemicals on top of the wings in order to prevent this kind of ice formation on the plane. And therefore, maybe with probably, and we have already got results that these kind of structures can prevent from that, removing this kind of this type of additional treatment. Another very nice example is connectors in the car. There is a huge amount of electrical connectors in the car. It's around 1,000, almost 2,000, and which is almost which is a huge amount. And therefore, cars when broke, it's often not because of the engine problems or something. It's because of these electrical connectors. This is the most often failure in the cars. And for example, this Audi A8, I forgot to tell you, it's this electrical. There is 2,000 electrical components in this car. So by structuring these electrical components with this technique, we are able to increase the insertion force, so it slides much easier, so that you can build more contents into the single plug. And also we reduce the electric resistance up to 8%. So now we are working on the pilot machine, which will be able to structure these 2,300 connectors per only 40 seconds, which is required for this Audi A8 car. And we also calculated that it will cost 0.21 cent per one car. It is not so expensive. So this is not a very expensive additional cost at all. And we are already working on it because of the corona. Of course, it's a little bit postponed, but we already have a pilot plan. And this was done together with our partners from Fraunhofer and Material Engineering Center Saarland, where they developed this technology and tested the electrical contact properties. And you see, this is the fabrication line being able to do that. And for this, we have even created the company that are working in order to present this or realize this production in industry, which is called SurFunction. So another way to get closer to the industry is using a roll-to-roll hot embossing technique. This technique is hugely used in the industry. For example, you can see there is in fashion industry, this artificial or leather creation. They have different kind of structures. And this, or even in shoes, you can see different structures. They all are made by this technology, which is based on, as you can see here, some flexible material is rolling through the two drums, which presses this material, and one of the drum is structured. And therefore, you can transfer that structure on top of the material. So continuing with the application, can be in furniture. It's also made in similar manner. Those layers on top of the furniture plates are made in this kind of technology. Packaging, huge amount of the automotive applications, like panels. They are also structured in this way, or leather on the car seats. So it would be really cool if we would be able to come to this area with the laser techniques. And therefore, what we do, we developed a machine that is able to structure this kind of drums. And we have that kind of machine in our lab, build it, and is able to structure these drums with much smaller prices. Usually, for company to buy this kind of drum, is a huge amount of money, especially depending on the complexity of the structure, can go up to 200,000 euros. And with this technique, we can go down to 400, 500 euros per drum. And here you can see the real process, which you can see the real process of drum structuring. This is in real time, so it's only 50 minutes required to structure the drum. And for example, with electron beam, it's sometimes you need 1 week to structure the drum. So this, you can see how shiny colors appears, these rainbow colors, because of the tiny structure on the top of the drum. So even we can not only cover the whole structure, we can create images, and therefore with the colorful images that I showed you before, all of these kind of images can also be created on the drum and transferred into the imprint process. As you can see here, this kind of roll-to-roll imprint system, which we also have in TU Dresden, so that we can test our structured drums by using roll-to-roll hot embossing technique. This is the part responsible for the hot embossing, and here you can see the video from the inside from this machine, how those images are transferred to the flexible material, which is in this case is a polymer foil, and we can go into huge speeds which can go to 15 square meters per minute. So what's next? I also want to introduce you the project that we are working on. It's a Horizon 2020 finance project called LAMPAS. And with this project, we try to go further in the field of our technique, bringing it to the even faster speeds, where we combine together different kind of companies. First, that produces lasers, very powerful one, 1.5 kilowatts is one of the most powerful pulsed lasers. Then we have some optical producers that produces optics for fast scanning of that beam. There are some companies that work on monitoring of the process, and of course we as a DLAP produce these technology producers, and we want to combine all of them in order to be able to create a system that will will combine that together and will be able to implement all of that laser power that is coming from that huge amount of laser power into the material by distributing it really fast and bringing this technology to the next level of fabricating speed. So in this Horizon 2020 LAMPAS project, we are trying to achieve those goals. And with this, I would like to conclude my talk, and I would be happily to answer answer any questions from you. Thank you.
Well, thank you, Dr. Wojciech, for really interesting presentation. We have a couple of questions for you, but before that, I would like to remind the listeners that you can also give questions to Mr. Wojciech. Just use the chat in the YouTube live stream. So the first question is, how expensive is such laser?
Well, lasers, of course, it depends from which perspective you look. From the industrial perspective, it's not really expensive. Those companies buy a huge amount of those lasers. For them, it's not a problem to buy. But of course, this it depends again on the laser, but usually it can be from few tens of thousands euros up to few hundred of thousands of euros. It depends on which kind of laser or the pulse duration you use. For example, those nanosecond lasers, they are already a long time in the industry. So the pulse durations is nanosecond, which is relatively long. And therefore, these lasers are a little bit cheaper because it's cheaper to produce. So you can buy from few tens of thousands euros even. But this, they are really expensive, which is femtosecond laser, especially if you need to build very small and tiny features. With this 400 nanometer, for example, you have to use femtosecond laser, and these are much more expensive. Of course, there are also lasers which are even more cheap. You can buy them on in Chinese websites. You can buy the whole system for a few thousand of euros, but they are not pulsed lasers. They are continuous wave lasers. So there are no pulsing, and the laser just shines, which is not good because it just creates heating on the surface. You can modify the surface, you can melt the surface, you can even try to cut the surface, but the quality of that process will not be so good because it's the pulse of the laser. There is no pulse. The laser is just heating the surface locally, but still there is a lot of heat applied. Yeah.
Thank you for your answer. And the last question, because it seems we're out of time. How durable are these engravings? Are coatings necessary to preserve the patterns?
Well, of course, if you scratch them strongly with other material, with, for example, steel on top, you can definitely remove them. But we are also, because they also made from metal and so on. So if you use a stronger another metal or even another stronger material to remove them, for example, in the friction applications, when the contact is really how it's physical contact, they will be removed. But we are working on that in order to preserve these kind of structures. Maybe I can fastly show you one of the example. I think I have it. I think I have it here. So here, it's a nice picture. But to show that, for example, here you can see the structure, direct laser interference patterned structure, which is patterned on top of the bigger structure, which is made by simple technique, DLV, that I showed you in the very beginning of the presentation. So with a single beam, we create those holes, and inside those holes, we create the structure so that we can protect the structure. So when two materials, let's say, move like that in touch, the structure on top is being damaged, but the structure inside those craters are preserved, these DLIP structures. And this way we can keep that structure still inside and therefore keep the functionality of the surface.
So thank you for your answer, and especially for a really wonderful presentation. And now I'd like to introduce the second key speaker, Dr. Erik Källström, a professor at Swedish Meteorological and Hydrological Institute and adjunct professor at Stockholm University. His research is related to climate, its variability and change. Dr. Källström focuses on regional climate modeling and support for users of climate information. He has 80 publications indexed by Web of Science database that were cited almost 6,000 times. In his presentation, Erik will talk about application of large ensemble of regional climate model projections for Europe. Let's give the screen to Dr. Källström.
So thank you very much. I will just check that you can see my screen first. Is that okay?
Yes, we can clearly see it.
Excellent. Okay, good morning to everyone. As said, I will talk about climate change and regional climate change and how we can work with climate models to say something on climate change. And also, I will, of course, touch upon the energy sector as well. So the focus will be on Europe and especially Northern Europe. And but I will just start by just stating a few facts here that we know that climate is changing very rapidly, as you know. This is a picture of an observational station somewhere in Sweden. And in these stations, we do measure a lot of different things like wind speed on top of the mast there. And we have precipitation measurements and also temperature and some radiation and other stuff. And these measurements, they are really making up the grounds for what we know about climate change. And if you collect all of these measurements from Sweden and Europe and the whole globe, wherever we have observations, we can of course then reconstruct the evolution of the climate over the last 100 years or so. And this is from one such picture, and you've probably seen those many times. And this one is from NASA, so it's from a US data set, but it really covers the whole globe, so they have used all of the data available. And what we see here is the global mean temperature close to the surface level, and we can see this very strong increase that we know is then due to the increased greenhouse effect of the atmosphere due to emissions, especially of carbon dioxide, but also other greenhouse gases. If you look in some detail here, the red line is a smoothed line, so it gives you really a good picture of the trend. And the trend is such that the current rate is about 0.2 degrees centigrade per decade. So since around 1970 or so, we have had a 1 degree global warming actually. And it's a very quick warming we see. So this is on the global mean, and you can see here also some features like these blue bars here saying something about the uncertainties that were larger in the beginning and they are smaller now when we have more observations, etc. This is not just on the global scale, of course. We also see these differences regionally, and in the background you have a map here showing the pattern of this warming over the 20th century, basically. So that's from one of the special reports from IPCC a couple of years ago. And also if you go down to the really smaller level like Sweden here, we are comparing two 30-year periods. And if you start looking at details here, you can see we have a 1 degree warming also in Sweden over this time frame here. And you can really see these colored, the isolines are moving towards the north. So climate is changing very rapidly here. And it's not just temperature, it's also things like precipitation are changing in different parts. And here in Northern Europe, we see more precipitation in the last decades compared to previously. So there is definitely a lot of change ongoing. And then the question is, of course, what will happen in the future? And this is where climate models come in, since we need them to say something about conditions in the future. But the future is extremely uncertain, of course. We don't know where to end up here. These are results from a number of global climate models. And the large uncertainty here, the difference between these colored lines here and the colored areas, this is different emission scenarios. And that has to do with the fact that we don't know about the future. What will the carbon dioxide emissions be? That's uncertain and that's unknown. So we use a range of different scenarios, from scenarios with ever increasing and strongly increasing emissions, but also other scenarios with the strong mitigation. So there is a wide span here, as you can see in this figure, what might happen in the future. So we might end up at different levels here, 1, 2, 3 degrees, etc. And there are targets for this, also political, to try to keep emissions so low so we don't reach 2 degrees and preferably not even 1.5 degree warming. This warming, it manifests according to the climate models. I will get back to them in a minute, but this is what it looks like. So if you look at the global climate change pattern, it looks like this basically. So this is now from two of the scenarios that I showed in the previous picture, the blue one at the bottom and the red one on top here. So we can then see how these changes manifest over the globe. And this maps compares a lot to the other one I showed just a minute ago about the observations. So we see stronger changes over the continents compared to over the oceans. And we also see a very strong change in the far north in the Arctic area. And these stronger changes over the continents and over the Arctic area, it relates to first, over the Arctic, it's about snow cover and ice. So when it gets warmer, there is less snow and ice on the ground. And that means that this very white and reflective surface we have in a colder climate, it disappears, and therefore more of the incoming radiation from the sun can really stay and get absorbed by the system and also increase then the temperatures. So when the snow disappears, it gets rapidly warmer, and that's what we see in the north. And over the continents, the warming is more rapid over continents compared to over the oceans, as in over the oceans, the temperature increase and the warming, it needs to really penetrate into very deep layers of water, and that takes a long time. So that's why warming is slower over the oceans. But the patterns are very similar here, even if we go for the low end emissions or the high end. And similarly also for precipitation, then we can see here that there is an intensification of the hydrological cycle actually. So in areas where we do have a lot of precipitation, like in the tropics, in the rain belt there, and also over mid latitudes, like here in Europe, for instance, there are greenish colors or bluish colors on these maps, and that's where precipitation is increasing in the scenarios. While in other areas like the subtropic areas, and this would be over the Mediterranean area, it would be over some desert areas in Southern Africa, for instance, as you can see here on the maps. These are areas where that will become even drier in the future, actually. So this might sound, the reason for the more intensified hydrological cycle, it has to do with the fact that warmer air can simply hold more water vapor. So there is more evaporation from the oceans and thereby also more precipitation. But in dry areas where there is no precipitation, then the stronger evaporation will lead to even drier conditions. So this is what we have in front of us. And you can also see in these maps that there was a lot of strange symbols here, like stipplings and dots, etc. And that has to do with some, where we have statistically significant signals or not. And in these areas that are hatched, like you can see a band over Central Europe, for instance, there is an uncertainty there whether we would see more or less precipitation. Actually, different models tell a slightly different story. And this, of course, has a very strong impact on anyone who are interested in conditions in exactly these areas. Will there be more or less precipitation in, for instance, the Baltic Sea region? That's not so certain, especially not for summer. I will get back to that later. So we see that. We also see changing extremes, so extreme conditions. We have these two curves here. It's just a sketch illustrating what can happen if we go from the colder blue climate to a warmer red climate. And this is then probability density functions with likelihoods of could be temperature, for instance. So if we go to this warmer red climate, we would see a higher probability, this red area to the right, of warm extremes and warm episodes. But we would also see less of the cold ones. And this is something actually that has already been observed quite a lot. So we do not have as intense and strong cold episodes anymore as we had before. And we also do have more extreme and warm episodes. So that's one of the most clear changes we see when it comes to extreme conditions globally, actually. I've also written a couple of things here to the left on top. Actually, if you're interested in really rare events, I mean things like return periods of say 100 or thousands of years or something like that very seldom happen. We have to keep in mind here that we don't even always have good observations, since it requires large data sets really to say something with some significance to it. So all assessments when it comes to such really extreme events are quite uncertain, and it's also uncertain to say very much about what might happen in the future. And especially if you're interested in so-called compound events, when there are two things happening at the same time. It could be, for instance, if you have very strong precipitation over an area and you have a high flow in a river, and then at the same time you get a windstorm piling up water in the ocean outside, and then that might be very difficult conditions in the cities lying where this river gets into the ocean. And assessing extremes and return periods for such episodes is very uncertain, actually. But by and large, we see more of the warm and less of the cold extremes. We also see more wet and more dry extremes at the same time, actually. Not at the same place, but happening in terms of when the climate gets warmer. And that has to do with the intensification of the hydrological cycle, as I just talked about a few minutes ago. When it comes to wind extremes, it's more uncertain, but we don't see strong signals of very strong differences in the wind climate, actually, in the climate models. So that's some basics what we see from the climate model. So then the question is, what is a climate model? And I will actually spend a couple of minutes here just describing this very shortly, so you have an idea about what these climate models are and how they work. So a climate model, of course, it needs to describe the climate system, and this is depicted here in this picture. So we can see there are different parts. We do have the atmosphere, of course, quite naturally, but we also have to take into account what's happening in the oceans, in the ground, and also in lakes and other water bodies. And we also need to know what's happening with, for instance, vegetation, since vegetation is kind of part of the climate system as well. So we need to, in these models, describe all of these different systems, the processes in them that are relevant. In the wind, in the atmosphere, it could, for instance, be wind. It could be low pressure systems, clouds, precipitation. But it's also very important to describe the fluxes at the surface. So this could be then sensible and latent heat fluxes, that is evaporation and precipitation. And we need to know all of these processes and describe them in these models. And then when we want to calculate this and make some climate projections, we need to set up some kind of grid where we calculate a lot of things. And we do that in a way like this. We set up some volumes or grid boxes in the atmosphere, and they can be of different size. And we do that both in the atmosphere, you can see that to the right here, and also in the oceans. All of these different grid boxes, they are then connected to each other, and for each of them we solve a number of equations, and that's what's listed to the left there for the atmosphere. So we can make calculations and calculate time tendencies of what will happen in a short while, given what we know about the state in the first place. And this is exactly the way that weather prediction models work also. We start from today's weather, we know what the tendencies are, we know if there is a warm wind coming from the south and how that might influence the temperatures. We know what will happen if the sun is above the horizon or below. So we can formulate all of these things in equations, and then we can make the calculations in the models. And the models are then, of course, formulated as computer codes, and these are codes with hundreds of thousands of lines, basically, and they are quite heavy things to run on the supercomputers. So we have a problem here with the model grid. I talked about the grid boxes, and these, if you just look at these maps for a short while here, so to the left we have a grid over the globe at 2-degree resolution, and you can see on that map that it's quite coarse. So Northern Europe, Scandinavia, the Baltic Sea, it's very coarsely represented, and there are even places that are more or less not existing in such a model, that is land areas in the real world that become an ocean, etc., and the other way around. And then if you go to the right and to the rightmost map there, we are down to about 12-kilometer grid resolution. And now it looks much more like the real map. And also, if you look at the colors, we can see that the height of the mountains, this is what's indicated here, it's much, much better represented at such high resolution. So for us living in Sweden, to the east of the Scandinavian mountains, this is extremely important for climate, since most of the precipitation actually ends up on the west side of that mountain range. And if the mountains are not there, like in the leftmost plot, too much of the precipitation really spills over and ends up in Scandinavia or in Sweden instead. So these things are things we need really to take into account in our models. And then I can say that the typical grid spacing in the global climate models that are underlying the IPCC reports, I've written some acronyms up here, CMIP5 and CMIP6. These are very large global experiments with these models. They are typically of the order of a couple of 100 kilometers, and sometimes a little bit better, but they're still quite coarse. So that means that they don't really represent these processes in the very best way. But then if we go down to regional climate models that I will talk more about later, then we are in that right map there. And you can also just overlay here a weather satellite picture illustrating also the systems that we want to simulate with these models. So it's also quite clear here that with a very coarse resolution like the one to the left, we can't really represent these, for instance, these low pressure areas and clouds in a very realistic way. So we need to have better resolution to do the details here. And this, the problem, of course, is the computational power. And every time you double the grid size here, or half the distance between the grid points, you're increasing the number of the computing cost 8 times, since you also need to double the time or half the time step. So going from the left here to the right, it's almost a factor of 6,000 when it comes to the computational costs. So that's really immense computational costs. And that means that we can't do too much on the very high resolution. So what we try to do here is we try to use regional models, where we run the models with higher resolutions for a smaller limited area. That could be Europe, and then we can go to the final resolution and do some more detailed impact studies in some area where we want to address some results. So to the right there is the area of Stockholm. It's like a 50 by 50 kilometer, and with the highest resolution models that I will talk about now, we are down at the greenish, the green dashed grid here, basically. So what can now these climate models tell us about the future climate? So I will briefly show a couple of results from a very large experiment with many such regional climate models that I just talked about at 12-kilometer resolution for Europe. So they have a fairly realistic representation of mountains and land-sea contrasts, etc. But I will just reiterate here that we have a very strong warming anticipated ahead. And this diagram is from something called the Climate Action Tracker. And it's a thermometer there where we can look at the global mean warming since pre-industrial times. And we are now where the big arrow is at a little bit more than 1 degree warming. And the target of the Paris Treaty is 1.5. That's between green and yellow. And but currently, with the current policies, etc., we are somewhere in the blue bars up there in the uppermost part of the diagram. So warming more around 3 degrees is what seems plausible. And many of these pledges and targets, and they require strong increase in carbon uptake, for instance, with techniques that are not yet really developed. So we have a strong warming ahead. And with the current rate of warming, we reach 1.5 degrees in about 20 years from now, and 2 degrees in another 25 years or so. And what happens at the end of the century, we don't really know. So we can then just quickly look at these global warming levels. So we will really experience these global warming levels. So this is now a result from one such global climate model, where we look at the smoothed evolution, so 30-year running mean curve, comparing the pre-industrial, the yellow box there to the left, to the green and blue boxes. That's when we reach 1.5 or 2 degrees. So we can take the climate from such integrations and look at different time windows. And this is what is done here. So this is a lot of maps. I will show a couple of pictures like this, just briefly showing some of the results. And this is now with these high resolution regional models, as I talked about before. So here we can see at different global climate, different global warming levels. These are the numbers on top there. So ranging from 1.5 and 2 up, even all the way up to 4 degrees global warming. And the temperature increases here are relative to reference period that was at the end of the 20th century. So it's quite recent. So we see an increase in temperature. This is the top row, more and more red colors, and especially up in the far north and also in the Mediterranean area, especially in summer. So there's a difference between summer and winter conditions. The second row tells us something about how many days there are every winter. This is now December, January, February, when the temperature is very close to 0 degrees. So when we have both plus and minus degrees in the same day. And these are days when you can have quite problematic conditions, like you can have slippery roads, or you can have a lot of ice and meltings, freeze and melting episodes. And this can have impacts on infrastructure and also on power cables, etc. So there's, and here we see, even if it gets warmer, we can see that in the far north, these conditions might actually become worse, at least in the winter months in the future. So we go from a very cold climate to this more mild climate. The two lower rows show what might happen to precipitation, and there is an increase in Northern Europe, green colors in both of these maps. But you can also see that in summer, the third row from the top, that this increase is is only in the far north, in Scandinavia and in Northern Europe, but not in the Central and Southern Europe. And this line then between increasing and decreasing precipitation, it's quite uncertain, and models give slightly different results here. If you go on then, we can then just look at projected changes for the end of the century. And this is for one area. This is the Baltic Sea runoff area. So here we compare both temperature increases and precipitation change. So temperature increases on the x-axis and precipitation change on the y-axis. And there is a large number of different simulations here in this plot, and they then indicate that it will be warmer, of course, but also here in winter, more precipitation. So these plots are you can see there is an increase in precipitation with time. There are different acronyms down here, and these are different scenarios. And this is what this really tells us. So mitigation here matters very strongly. So if we go for the low end scenarios to the left or the high end scenarios to the right, there is a very, very strong difference in future climate change signals. So this is important to keep that in mind. Some more results then for precipitation again. The top row tells us about maximum precipitation over a week, and this could be interesting for flooding events, for instance, and there we see a strong increase everywhere in Europe, basically on an annual mean basis. So there is a larger risk than for more strong water and river runoff episodes. The second row here tells us something about effective precipitation. This is precipitation minus evaporation. And even if precipitation then increases in summer, we also see stronger and warmer temperatures, so then also evaporation increases. And that means that if you now look at the Baltic Sea area and southern Scandinavia and the southern part of the Baltic states, we see that there are some brownish colors here and there that indicates that it might even become drier conditions. So what we see in front of us here is that there might be stronger differences between wet and dry years actually in the future. The bottom row indicates maximum snowfall in intensity, and snowfall is decreasing in most places. But if you look carefully in the high parts of the mountains, the high altitude areas, where it's still cold enough and when there is more water vapor in the air, we might actually get stronger snowfall intensity events in the future. So strong snowfall events is not to be excluded in the future climate. We might see that also in a warmer climate, especially in high altitude areas. But when there is a snowstorm coming around, it might become more intense in the future. Oh, sorry, went the wrong direction. So then for wind speed, and as I said before, it's a bit uncertain here. So we have the mean wind speed here in the two topmost rows, and the topmost row is as close to the ground level. So this is 10 meters above the ground. And in all of these maps, there is an increase over the Baltic Sea actually, while there are decreases in large areas around. And if you look at the next row, we look at the higher level here, a couple of 100 meters up in the air. And there you can see more of the increase also in larger areas. And this increase close to the ocean or to the Baltic Sea, it is probably related to the fact that the Baltic Sea becomes warmer. There will be less sea ice, and that means that there will be more of a mixing of air from the higher levels and thereby slightly higher wind speeds. The bottom row, which might be important for wind power, indicates that there is a tendency for slightly more calm days with very little wind speed in the future, but these tendencies are quite small, but more in the Mediterranean area, as you can see there. So summarizing the climate change part, and then I will just quickly get into the impacts on the energy sector. We will see, and I didn't say that, but we will see a continuous, very variable weather and climate up here in Northern Europe, with differences between warm and cold and dry and wet years, for instance. We will see continued warming, especially winter, more precipitation, again, especially winter, but there is then an increased risk of drought and dry conditions in the dry years. Temperature extremes will also change, with more of the warm and less of the cold extremes in all seasons, and especially when snow cover is retreating and disappearing, there might be very large differences in the temperature climate. more pronounced precipitation extremes, and then it's a bit more unclear about exactly what might happen to the wind climate. So what are the impacts then on the energy sector of all of this? I will just give a couple of short examples here, and there is of course a lot of things to say about it, but I will maybe start here to say that the demand for energy will change, and especially if you look at the heating demand, that is something that will decrease a lot, and these are just two plots from one simulation indicating such a decrease in the number of heating degree days over time. This is a quite strong emission scenario, so there is a strong reduction in the heating requirement. At the same time, of course, in summer there is a increasing demand for cooling as it gets warmer, so there might be, at least in warm episodes, more needs for air conditioning, etc. We see a longer vegetation period, and these are observations from Sweden already indicating that we have over the last decade seen a couple of weeks more longer vegetation period defined by some temperature criteria here. And this is what's also seen, this is again just one scenario, not all of the models I showed before, also indicating increases here of up to several months actually at the end of the century under a strong emission scenario. So this might be beneficial for biomass production, but there are also side effects and negative impacts here, like the dry conditions I talked about. There might be really dry summer sometimes. We also know that some insects and pests might become more common here. So there are also disturbances and problems associated with this, of course. Hydropower conditions will also change. Here is just some hydrographs for a couple of scenarios for one river in northern Sweden, where the black line then is the control climate in the end of the 20th century, and all of the other lines are scenarios for the future. And in this river, they indicate an earlier snow melt, and the snow peak is earlier in spring, and it's also slightly smaller in this case. There is less snow accumulated over the winter that can melt. But there are also stronger flows and river flow in the winter season, and so there are differences, and this hydrograph curve would look different in different areas of Europe at different times. So there might be strong implications also for hydropower. For wind power, it's a bit more uncertain what will happen about the large-scale changes in wind. We see less sea ice and snow, as I said, and that might result in fewer days with really calm conditions over the ocean, like the Baltic Sea. Of course, less icing in general, but in some areas in winter, there might be more conditions with temperatures close to zero, which might be problematic for the wind power, but also for the power grids, for instance. So this is something to consider. Finally, about disturbances, just one example, also maybe mostly related to the power grid, but also to other systems in society. We are thinking about lightning here, and to the right are some maps, a map just showing the number of days with lightning in the post climate. And then the question is, with more vigorous convection, these very strong clouds and heavy rainfall events, showers in the future, will there become more lightning events? And these two curves here are from a student paper of mine, and she looked at that, and yes, we will see more of these very strong convection, strong heavy downpours and heavy rainfall extremes. But at the same time, there are other impacts here on the clouds with maybe less ice crystals. So the change in the lightning frequency is not as dramatic, but the curves in the lowermost graph indicate some increase also in lightning and the length of the season with lightning. So it might start a little bit earlier in spring and a little bit later in the fall, as we have the majority of the lightning events in the middle of the summer here in Northern Europe. So just a few bullet points here. This is my last slide. So we see then for the energy sector decreased demand for heating and increased maybe demand for cooling instead in summer. And if you look at Southern Europe, where we already have a quite strong demand for cooling, this will then be more of a strain on the energy system in the summer season. For the hydropower, actually in the north, we see probably an increased potential here for hydropower, but in southern most parts or Central Europe, this is maybe not the case everywhere. So there is a shift also geographically here from where we see more and less precipitation, more water in the magazines, etc. The biomass production, I talked about it. I also mentioned briefly the problems that might be associated with it, but we will of course have a longer vegetation period, that's for sure. And I just talked also about wind power. There is a question mark after increased, and this might be, we don't exactly know what will happen. And also storminess is quite uncertain. There are indications in the climate models that the worst storms might become even worse, but on the other hand, that the frequency might not be that strong. But this is still to be analyzed further, and we don't really know there. I didn't talk about it, but solar power might decrease in the future as these more humid conditions in the future climate seems to lead to more clouds and more cloud cover, and that means less incoming solar radiation. So some decreases here in the potential for solar power. It's not that it's going to be, of course, cloudy every day, but there are some decreases. And we also, other impacts here, the second last bullet there about cooling water is something we see, of course, also. So if we have power plants like along the coast of the Baltic Sea or along rivers, the cooling water is definitely going to be warmer, and that might become a problem in some instances. And my last bullet point down there, this is where I want to end really, and I want to say an emphasis that all energy systems, especially those that are associated with renewable energy, I think there is a requirement for adaptation, and if you plan such energy systems and want to build out something, then you need to consider and think about what the climate might be in the future. So don't plan for the future, your energy systems for the future based on yesterday's climate. I think we should use climate model results here to help us and guide those decisions. And by that, I would like to say thank you very much, and I'm also open to any questions. Thanks.
Thank you, Kjellström, for your interesting presentation. You received several questions. However, I'd ask you to just answer them very briefly, as we should start with the next presentation. So the first question is that one listener is wondering how Green Deal EU program could change the scenarios.
Yeah, I think, as I said before, mitigation is extremely important, and all projects and where you really put emphasis in reducing emissions, it doesn't really matter what it is, it's really beneficial. So all of that can really be of importance. So it's about reducing emissions, but it's also, of course, about reducing the requirement for energy and the energy use. So it's both reducing demand, but also reducing the emissions in the energy production itself. So there are different things there. Yeah.
Okay, so the second question is, by these scenarios, how nature will change, how plants and other live organisms will adapt to these changes?
I think this is a very good question, and the climate change signal that we see and that we foresee in the scenarios, it's very, very rapid. So some plants and some living organisms can of course adapt to that, but others cannot really. So that's also depending on different regions, and in some areas the changes are so quick, so some ecosystems will likely not be able to survive basically, and others will just move towards the north. And if we look at, for instance, in Sweden, in the mountains, we see that tree line is growing up in the hills, and at some point we will not see the open mountain tops anymore, basically. So these are the things that will happen. So there is a strong and quick change there.
Okay, so the third question is it already known when the new IPCC approval climate scenarios will be announced, and when simulations of regional climate models according to them could be expected?
Okay, so IPCC will come out with a new report in this summer, likely early August, and they are assessing all of the scientific literature. So in fact, IPCC don't have any climate scenarios, but they are presenting research based on climate scenarios made by climate researchers. So these are type of the models that I showed before here. So many of these scenarios are already out there, and they have been in the literature for a few years now. And when it comes to the regional climate models, we have still been, all of the results I showed on the regional scale, those are based on the previous generation of global climate models. So we don't have any new scenarios expected. But the question is here when we can expect them. I would say in a year or two, the first regional climate model scenarios based on the new IPCC and on the new scenarios presented in the next IPCC report will be there.
And the last question is, I fully understand that to develop such models, you need an immense amount of data. How difficult is to acquire the data? Are there open source data sources available?
Yeah, I think for the models, once you have set a model up, then you can just run it. You don't need too much data to run the model. But of course, to evaluate the models and to build and also to monitor what's happening, you need a lot of data. And there is a lot of data available, actually. For instance, much of it is collected via the Copernicus Climate Change Services. They have a data store where they are really putting in a lot of information, both from remote sensing data, that's satellite and radar, etc., but also from in situ measurements. But it's right, it requires a very strong international collaboration on these observations, and also to keep up old measurement stations in different countries to have those observations and assure that we have long time series, since that's of course important in climate.
So once again, I'd like to thank you, Dr. Kjellström, for your answers and of course, wonderful presentation. And now we would like to move to the third key speaker and the last one before the lunch break, Dr. Ana Luisa Fernando, an associate professor in Nova University, Lisbon, a true expert on energy crops with more than 25 years of experience. She has a special interest in the sustainability of energy crops production. Dr. Fernando is either author or co-author of 3 books, 47 articles in peer-reviewed journals, and 128 articles in various conferences, a national coordinator of 3 Horizon projects. Today, she will give a presentation on cultivation of energy crops in marginal soils. Dr. Fernando, when you're ready.
Good morning, everybody. Thanks for the invitation to come here and to present this work. And I will just move forward to the presentation. And please advise me if I'm taking too much longer than what is supposed, because sometimes I intend to talk a lot about these issues. And so the talk will be on the cultivation of energy crops in marginal soils, and we will see what is the economic or the opportunities and risks associated with this cultivation. And we will have a look into the technological, environmental, social, and economic issues. So we know that the development of commercially viable green products based on natural resources, namely, for example, on biomass, they have a lot of wide range applications. And those applications can be to energy, to biofuels, to biomaterials, to a lot of different products. And they are gaining more and more increased importance, especially with the Green Deal. And we know that energy crops and industrial crops, they are really promising because they have very high productivities and also different biomasses. They have different characteristics which make them very interesting for the substitution of fossil origin products, namely biofuels, but also, for example, plastics, etc. And some of those industrial crops can be sugar crops, like sugarcane, sweet sorghum, sugar beet, but we have also oil crops, namely some rapeseed, sunflower, and also jatropha, which is more in tropics, soy, and some lignocellulosic crops like bamboo and miscanthus, and also in the Mediterranean area, cardoon. and fiber crops, of course, because fiber crops, they are very interesting for fiber products, namely flax and knaf, but also hemp and cotton. And then we have the starch-rich crops, which are also food crops, namely wheat, corn, and potato. But the problem is that if we are going to increase the demand for biomass, for bioenergy, and for byproducts, we will have an increased competition for land. And this means that maybe it's more interesting if we can grow the dedicated biomass crops for biofuels, for bioenergy, and for byproducts in marginal soils, because this will limit the ethical issues associated with competition with food crop. But the problem is, if you're going to grow these dedicated biomass crops in marginal soils, if they are marginal, it means that maybe the yields are not so good. And the question is it feasible to do it? And this is the aim of the study, to try to evaluate what will be the technological, the environmental, the social and economic opportunities and risks of cultivating energy crops in marginal soils. And here are some of the results that we collected in many papers that are dealing with this issue. We will have the yields, and in terms of the yields, we have different yields, and usually the yields will decrease if we move to marginal soils. And here we see that, for example, for 4 different types of perennials, for example, cardoon, giant reed, switchgrass, and miscanthus, we see that we have reduced yields when we increase the marginality of the soils. And this is a marginal soil that has natural constraints, and this is a very heavy marginal soil with very heavy marginal conditions. But still we have some biomass, of course. But the problem is that when we have a lower yield, this will limit a lot of other issues and a lot of other parameters. For example, lower yields will reduce the non-renewable energy savings, and it will reduce also the greenhouse gas emission savings, and even in terms of the chemical composition, because we will have lower yield, and so the amount of biomass that is growing in a certain area, it will be lower. Maybe we will have a concentration of some elements such as nitrogen, phosphorus, and potassium. And also there is this problem that maybe the plants may not reach a mature status. And this is important, for example, for perennials, because maybe if they don't reach the mature status, maybe some of the elements will not go to the rhizomes at the end of the growing season. Another issue is that if we are going to reduce the yields, the amount of land use to obtain the same energy output, we will need a higher land area. Also, if regarding the marginality of the soils, we may need a higher amount of fertilizers per unit land, and this will have a problem in terms of economics, because we need to buy more fertilizers. But also, especially nitrogen fertilizer will increase the greenhouse gas emissions, and so the balance may not be as good as we want. And also, in terms of biodiversity, we will have a lowered shelter for animals. Perhaps the energy production costs will be increased, the greenhouse gas emissions reduction costs will be increased, and this is only to name some of the few risks that we will face by cultivating energy crops in marginal conditions. Let's see some of the results. For example, for the same work, we compared the non-renewable energy savings that we could evaluate for those 4 crops, cardoon, giant reed, switchgrass, and miscanthus. So we know that the yields were lower, and also when we compare the fossil energy saved to what we were able to save in standard soils, we see that there was a reduction in the non-renewable energy savings. But still, even in the most marginal soils conditions, we can have still a positive non-renewable energy savings, which is interesting to contribute to the Green Deal. Also, in terms of greenhouse gas emission savings, let me just connect my battery, otherwise I will be muted. So in terms of greenhouse gas emission savings, also, even in the most marginal conditions, we still have a positive greenhouse gas emission savings, but much lower than what we see in the standard soils. In terms of land use, okay, to produce the same amount of feedstock to feed some bioenergy plants, power plants, etc., we will need a higher land use, which means that in terms of logistics, these may even contribute to have some problematic issues. But anyway, it is something that we should deal with. Of course, in terms of marginality, because we will have lower yields, the energy production costs is increasing. And this means that the break-even delivery price in terms of euros per megagram that we are going to produce is going to increase. This is a study that we've made with miscanthus in zinc-contaminated soils. And we know that because the yields reduced when we moved from a standard soil to soils that were contaminated with zinc, the lower yields meant that in terms of energy production costs, we needed to increase the amount of costs to produce the same amount of ton per hectare. And also, when we try to evaluate how much is the cost of the greenhouse gas emissions reduction in terms of euros per megagram of CO2 that can be somehow abated, because also we will have lower yields and because we will need more area, and so we will need to spend more money in terms of fertilizers, the machinery, everything. We also see that the costs of the greenhouse gas emission reduction is increasing, and this may afterwards be not so beneficial. But anyway, it's a cost that maybe we need to get. And this is something for the Green Deal to think if it is possible to have some sort of grants that can help to contribute to boost these type of biomasses to contribute to the greenhouse gas emissions reduction. Then what is happening with biomass characteristics? Because we know that if we are going to have lower yields, maybe, as I mentioned before, maybe we'll have a higher increment of some ash content, for example, nitrogen content, phosphorus content, potassium content. And some of those increments may limit the industrial use of this biomass. For example, in combustion plants, the ash content is really a problem. And we see, okay, this is a pilot study, but we know that, for example, in this study where we reduced the amount of water availability that we gave to the plants, we saw that, for example, when we reduced the amount of water from the total amount that the plant needed to about a quarter of what the plant was needing, we saw that the yields reduced, but also the ash content in the biomass increased. And this means that in a combustion power plant, if we will have a higher ash content, then this is a residue that we need to deal with, and an increased amount of ash content means that we'll have a higher amount of residues to treat, and this may represent some problem. Also, in this study, we also test dry and treat in the different soils contaminated with zinc. And compared to the standard soils, we see, for example, in the stems, but also in the leaves, that there was an increment in the ash content. And this increment in the ash content was not only because the yields were reduced, but also because there was a higher concentration of minerals in the biomass and also zinc in the biomass. And this may also contribute to limit the industrial use. Because if you are going to have a lot of ash content, this means that we'll have to deal with the amount of residues that are coming from the use of this biomass. This is why it is important to think which sort of techniques are most appropriate for a biomass that is coming from marginal soil or that is coming from contaminated soil. Perhaps combustion is not the best solution. And for example, gasification, that is a technique that allows that the biomass is not so clean in terms of some of the elements, such as the ash content, but also such as the nitrogen, or for example, the potassium. Maybe it's a more interesting crop to be used or technique to be used to obtain energy from these biomasses that are coming from soils that present some marginality. Okay, some more studies. The biomass characteristics in terms of the amount of nitrogen. And this again was a study where we studied miscanthus in zinc contaminated soils. So in this case, it was a standard soil. And then we had the biomass coming from soils contaminated with zinc at a level of 450 milligrams per kilo and 900 milligrams per kilo. And we wanted to understand how much was the nitrogen content in the stems, and also how much of nitrogen was taken out from the field in terms of kilograms per hectare. And when we see in terms of how much emissions of nitrogen we could have by the combustion of these stems, we see that it was not a problem in terms of the composition, because the amount of NOx that were emitted during the combustion of the solid fuel was more or less the same for the different types of soils. So we didn't saw a higher content in nitrogen in the biomass that was coming from these marginal soils, which is good, because in this way we will not contribute to a higher amount of NOx that will be emitted. And NOx is a problem in terms of environmental pollution. But let's see what was happening in terms of the nitrogen application. Because those soils were marginal, we needed to put an extra amount of nitrogen fertilizer. And when we put nitrogen fertilizer in the fields, we know immediately that there will be some volatilization of ammonia and also some oxides of nitrogen. And these will contribute to the acidification and also to the greenhouse gas emissions. Also, the amount of nitrogen that we apply will contribute to the leaching and runoff of ammonia and also to nitrates. And these can contaminate the ground and surface waters, contributing to the eutrophication and also to the excess of nitrates in drinking water. And this is really a threat to the human health. Also, part of this nitrogen that is applied in the soil will denitrificate to nitrous oxides, and this will contribute to the greenhouse effect and to the ozone depletion. So this means that in this case, in those contaminated soils, because we needed to put extra amount of nitrogen in the fields, this contributed to a higher ammonia and NOx emissions, also to the higher ammonium ion and nitrate emissions to the groundwater and also by runoff to the surface water. And also this contributed to a higher N2O emissions. And this may represent a problem in the overall opportunity and risks associated with growing energy crops in marginal conditions. Also, because we will need a higher amount of nitrogen, this will reduce the energy balance, because nitrogen fertilizer is really an important issue in those energy balances. It will also contribute to reduce the greenhouse gas emission savings. It will increase the acidification potential, the eutrophication potential, and also the ozone depletion potential. So we need really to balance the pros and cons of using a higher amount of nitrogen, even if the yields will be lower. But okay, but we will also have some opportunities. Some of the opportunities are related with soil quality, and soil is really an important issue, and sometimes it's neglected when we are dealing with evaluating different impacts. And we know that by introducing a vegetative cover, this means that there will be a reduction of the erosion potential. And the erosion is really a problem in the Mediterranean, but also in the north of Europe. It's becoming more and more a problematic issue. And we know that by introducing this vegetative cover, especially in a marginal soil, this will improve the reduction of erosion potential. And this is really important. It will also incorporate or increase the organic matter in the soil, which is important to carbon sequestration, to improve the soil structure, to improve the soil organic matter, and also to restore some soil properties. And even, for example, in this case, this is a work that was done with miscanthus. For example, miscanthus in different types of marginality. And we know that, for example, in this case, because we have a carbon incorporation in the above ground biomass, we will have a lot of carbon that is sequestered in this biomass. Okay, this biomass is afterwards get out from the field, but we'll have, in this case of miscanthus, because it's a perennial grass, we'll have a lot of carbon sequestered in the rhizomes. And in this study, it was possible to see that during the lifetime of the miscanthus of system in the soil, we may have a lot of 12.5 to 13.5 megagrams per hectare that is sequestered in terms of carbon in the soil. The problem is that when we are going to get out these rhizomes from the soil, then this stored carbon will be released, and this may represent a problem. But also, if the leaves will follow in terms of the amount of carbon that is trapped in the leaves, we see that it is about 3.1, 3.9 megagrams per hectare per year. And this is important to recycle the carbon to the soil. And we see here, for example, there was not a statistical difference between miscanthus fields and parcels without crop, but after 34 months, we already saw some trend where we see some differences between the carbon in the topsoil. And also here, we also saw after 34 months some trend where we see that in the topsoil we will have more carbon than in the parcel of a soil that is, or in the horizon 40 centimeters below. Okay, some more opportunities. Even these biomasses, especially in soils contaminated, for example, with heavy metals, those crops, they can also be beneficial because maybe they have some phytoremediation ability. And usually we know that most of the energy crops, they have this phytoremediation capacity because they are very tolerant to a lot of not only marginal conditions, but also contamination conditions, namely heavy metals. For example, in this study, we studied giant weed in lead contaminated soils, and we saw, for example, that there was this capacity of giant weed to accumulate the lead that was in the soil into the biomass. And of course, okay, maybe we will need more than 30 years to remove all the contamination in the soil, but it's a slow process, okay, but it's a process where, combined with a lot of other environmental issues, it's really interesting. And above all, because in this process, we may have a biomass that still contributes, for example, to reduce the greenhouse gas emissions and the non-renewable energy use. In terms of biodiversity and landscape, we see that, for example, this is a contaminated area or a marginal area where we don't have any vegetation at all. Just compare it with Miscanthus field, where we may have a deer going, crossing this biomass. Of course, maybe in marginal conditions, we will not have this nice image. But anyway, by introducing a vegetative cover, this favors diversity and occurrence of soil fauna and microfauna. It will provide shelter for invertebrates, birds, mammals. It will provide a higher cover value for wildlife. Also in terms of landscape, because we will have a higher structural heterogeneity and aesthetics. This is beneficial, but anyway, we still need to think that also in marginal land, usually marginal land also sometimes harbor high levels of biodiversity or very unique and valuable components of biodiversity. For example, for food and medicinal resources for locals. So we need to think clearly in certain marginal conditions if we want to introduce a new biomass that maybe will limit this biodiversity that is already unique in this place. So to conclude, we know that sometimes, and most of the times, when we produce those energy crops in marginal conditions, we may have a productivity loss that will reduce the energy and the income and also the greenhouse gas savings. But there are also some very good opportunities in terms of improvement of soil quality, biological and landscape diversity. And so in the end, maybe we'll have a very interesting balance. So we need to have an adequacy between the type of marginality and the crop. And still, there are lots of options for improvement. For example, breeding strategies, plant herbuscular mycorrhizal symbiosis, and to have a good crop management options in terms of fertilizers, irrigation, etc., where afterwards the balance can be really improved. So I would like just to thank the MAGIC project and my unit, and thanks for the attention. And if you have any questions, please.
Well, thank you, Dr. Fernando, for your presentation. We have several questions for you. The first one is, what do you think about possibility of energy plants to be used as bio-based building materials?
Oh, they're very interesting option. I myself, I'm working on the use of those biomasses for the production, for example, of bioplastics, biocomposites, but also, for example, for some products for the civil construction. The civil construction itself, it's a sector that demands a lot of energy, and also the materials, they need a lot of energy. And if we can replace in some parts, or if we can introduce to some of the materials, bio-based materials, we will contribute to have, for example, a building that is more green. But also the benefit is that if we will have a bio-based product, we will have the carbon that was sequestered during the photosynthetic process. a longer time. This is something that I think it's really mandatory in Europe to have a clarification of this and to introduce this issue, because even the energy crops can be interesting to have this bio-based material where the carbon will be trapped for a longer period, and then in the end of the life cycle of this material, then it can be used for energy.
Thank you for the answer. The second question is, what kind of energy plants are suitable for biojet fuels? Plants with higher biomass of lignin and cellulose, or plants with higher concentration of sugars, or all plants?
Well, there's a line of research that addresses the lignocellulosic crops as a sort of lignin for this jet fuel, which is really interesting. And I think for the moment, I think it's the most promising line of research. But also I would say that some of the oil crops, maybe not the starch crops, but some of the oil crops, they are also, or they show some promises in terms of the type of oil that in characteristics of the oil that can afterwards be used for the jet fuel. But still we need more research, especially on the lignin line of research. For the moment, the lignin line of research seems more interesting because the yields coming from lignocellulosic crops are higher than the oil crops. But on the other hand, some of the oils that are coming from those oil crops, they are so interesting for the jet fuel that maybe in the near future we'll see the two lines of research going hand in hand, and maybe we'll have the two types of products coming out for the jet fuel.
Okay, and the last question is that you mentioned that increase of lead in biomass may be helpful, but isn't cause health hazard, as it may be the part of a crop.
Well, most of those energy crops, they are not food crops. So this does not reflect the problem in terms of increased toxicity along the for example, we are not going to use it's not going to, the value chain for food is not affected. This is an issue. Also, because most of those, for example, when we accumulate a lot of lead in this biomass, even if we are combusting this biomass, this lead will remain in the ash material, which means that, for example, if I have a biomass that is accumulating a lot of lead or a lot of copper, for example, that is a very valuable metal, we may even in the ash material collect, or with metallurgical tests, to collect those heavy metals and then to use them again in their own, for example, again for batteries, or when we are talking about copper, again for some wires of copper. So maybe this is an interesting issue. The problem is that, for example, in the leaves, and usually those crops, they are not interesting for animals in terms of they don't really like those leaves, which is also interesting. Otherwise, the animals that could be fed by those leaves, they could have those amounts of metals in their body. Maybe the problem is, for example, with oil crops, where the seeds, somehow the metals, if they reach the seeds, not the oil part, but for example, the cake part where there is this protein, maybe then seeds could intoxify, for example, birds and other animals that could feed from those seeds. So in those cases of oil crops that are being produced in soils that are contaminated with heavy metals, this is an issue that we should look like. And for example, in this magic project, we are testing different oil crops in contaminated soils. And until the moment, what we saw is that most of the contamination is in the leaves and in the stems and does not reach the seeds. So this is a good issue for using this biomass in contaminated soils.
Thank you, Dr. Ana Luisa Fernando, for your presentation. And of course, big thanks to all of our key speakers. Now we'll break for an hour, after which we continue with 4 presentations by Dr. Zigmas Balavičius, who will give a presentation on plasmonics from biosensing to nanolasers. Dr. Tommy J. Lindros will talk about decarbonization and electrification in Baltic countries and Northern Europe. Dr. Roman Antipenko, who will present advanced laser systems at ELI Beamlines facility. And the last presentation will be by Paula Pero Garcia about smarter communities. I'd like to notify that after the break, Dr. Vytautas Saksnas, a chief organizer of the CYSENI conference from 2016 to 2019, will continue as the chairman. As this is my goodbye, I would like to once again thank the guests, key speakers, and of course, most importantly, you participants for choosing CYSENI conference. I hope you will enjoy the rest of the conference. See ya.
So, good afternoon, dear participants, keynote speakers, and all other guests. Welcome back to the second section of our conference. And first of all, I would like to bring a little bit more clarity and introduce myself. So I'm Vytautas Akstinas, a member of the organizing committee of CYSENI 2021, and also a senior research associate at Lithuanian Energy Institute. And today I will try to moderate this keynote session. But due to the multiple requests, I would like to remind that this year we have a recorded high number of participants presentations. It is almost 178 from 29 countries. And in order to avoid connection problems and ensure the best watching experience, the decision was made to upload recorded presentations instead of having the live ones. But most of our participants in the first half of this day asked how they can access them. And I would like to remind that presentations are available on the CYSENI website all this week up to Friday. And to access them, go to cyseni.com, the section for participants, and then conference access. But if you don't have a password, which is required, then just fill a registration form in the visitor registration under the section for participants, and you will immediately get them. And then you can enjoy all the conference presentations in the sections energy, physical, and environmental sciences. And just find the topics that are target for you. Also, you can leave the comments and questions to the authors. There will be a comment box below each video, but the comments are manually moderated, so it might take some time before it became visible to everybody. Also, we will have an opportunity to give questions to the keynote speakers, but for that you need to use YouTube live chat. And if you don't see it, probably you are viewing it on the CYSENI website. Just go onto the YouTube and please ask whatever you want. But also I would like to add an important disclaimer that only questions relevant to the topic of presentation will be selected. And I wouldn't like to waste the time anymore. And let me introduce you the first keynote speaker, Dr. Zigmas Balevičius, the head of Plasmonics and Nanophotonics Laboratory at Center for Physical Sciences and Technology, Lithuania. And today he will give a presentation that is dedicated to the phenomenon of surface plasmon response and its applications in the field of optic biosensing, tunable photonic devices, and photonic-based nanolasers. And more about that, I would like to invite Dr. Zigmas for the presentation. So please, Professor, the floor is yours.
Thank you, Vytautas, for introduction. And I will share my presentation and try to start. I will talk about plasmonics and the application of plasmonics in biosensing and new generation of nanolasers. My presentation will consist from the three major parts. Basics of plasmonics, so plasmonic for biosensing and how plasmonic can be employed in the nanolasers. And small conclusions in the end. So, in generally, surface plasmon Polaritons are electromagnetic modes that arise from interaction between light and conduction electrons in the metals. And at the moment, we know various types of plasmonic resonances. So the most known of them is a surface plasmon resonance. So in other words, surface plasmon polaritons. Also localized surface plasmons. The other plasmonic excitations may be less known, but at the moment, a lot of people work in this field, and various types of hybrid plasmonic excitations and modes is developed and studied. So, so in general, light-matter interaction leads to surface plasmon polariton modes having greater momentum than light of the same frequency. So it means that we cannot directly excite just only from incident light the surface plasmon polaritons on the thin metal layer, and due to that, we can use some couplers. It can be the glass prism or some gratings, and what this optical element do is actually change the angle of the light line, and you can see here that where the light line is crossed with a dispersion line of surface plasmon polariton, at this energy we can excite surface plasmons, or in other words, surface electromagnetic waves. So surface electromagnetic waves electrical field decays exponentially in strength with distance away from the surface. Well, however, in some cases we can have such kind of plasmonic excitations which for which we no need special couplers. For example, if we have a periodic dielectric structure of 1D photonic crystal, also called Bragg mirror reflector, and with a thin metal layer, we can directly excite a so-called TAM plasmon polaritons, a slightly different mode from the surface plasmon polaritons. If we look to the left picture, this is, you can see the dispersion line of the TAM plasmon polaritons. And this dispersion line is always lies in the cone of the light line. So it means that it's always enough the momentum of the incident light to directly excite such type of plasmons, and which is in some cases is very useful and important. TAM plasmon polaritons are optical states similar to the electron states proposed by Soviet scientist Igor Tam, and due to that they are so-called TAM plasmon polaritons, which can occur in the energy band gap on a crystal surface. The stop band of the photonic crystal or periodic dielectric structure, you can see here, resembles the energy band gap due to the Bragg reflections in its periodic structure. So in general, the photons feel this periodic structure, feel this periodic lattice, like a lattice in the real crystal. So the electron feels the lattice of real crystal, and here the photons feel this periodic structure like a crystal. As I said, the wave vector of incident light is always larger than TAM plasmon polaritons, and these modes have a lower losses than conventional surface plasmon polaritons due to that they are propagate actually more propagate in the dielectric layer than in the gold. The major part is in dielectric layer, the losses is minimized. In some cases, we can excite simultaneously. Both. Okay, sorry, I not see. Okay, so if we compare these two excitations, you can see here that the width of the resonances is slightly different, and here we have a TAM plasma resonance which is much more narrow than the conventional surface plasma resonances. So this is an indication of lower losses. So in some cases, if we attach the periodic structure with the thin gold layer to the prism through the optical contact, we can simultaneously excite both these modes, and these modes, TAM plasma polaritons and surface plasma polaritons, they change the energy between each other. So here you can see the dispersion lines, the two branches of the hybrid plasmonic modes, that for TAM plasma and for surface plasma. We can see here that we have shifted in the energy in comparison with the single ones with green lines. These changes these shifts in the energy is a signature of a strong coupling regime, and strong coupling regime is modified frequencies of both plasmonic resonances compared with a separated single resonance. And due to strong coupling, the width of the plasmonic resonances become more narrow. And here, if we compare the single SPP and SPP branch, here you can see how we can change the losses with hybrid modes. It's become much more narrow, because the main issue in plasmonics, that due to the metal, we have rather high losses in the metals, and this is influenced very strongly the quality factor of the plasmonic resonances, and this is the main issue and disadvantage in many applications. So the paradigm of strong coupling is that of two coupled harmonic oscillators may become coupled if there's some way for them to exchange the energy. If the interaction is strong enough, the energy levels responsible for emission are also altered, what we can see in the previous picture, and they become inextricably linked with each other. In such coupled systems, the coupling strength between two harmonic oscillators exceeds the damping rate, and as a result, we have the new hybrid modes. So the energy exchange between these two components in the hybrid modes is less than 1 femtoseconds. So this leads to reduced losses and the narrowing of resonance. For example, if we have these two resonances, TAM plasma and surface plasma polariton, we can express it in the rather simple model with two oscillators, which have connection through the coupling strength. And the solution for this equation system would be hybridized frequency for the oscillators, and you can see it's given here two frequencies for TAM plasma resonances, for surface plasma resonance, and the coupling strength. However, the solution itself is not guaranteed the strong coupling between these two modes. The system is in strong coupling only when the parameter G is larger than the quarter of sum of width of resonance. So in general, plasmonic resonances, they are sensitive to the polarization state of light. Some of them just only excited at one polarization. So it is useful to use the characterization method and measurement method, which can analyze in detail the state of light polarization. And spectroscopic ellipsometry, or in general ellipsometry, measure the change of the state of polarization of light upon reflection on the sample surface. So if we have known polarization from the reflection, our polarization is changed, and we measured the changes of polarization, which is the characteristic of our sensing layer. As you can see before, and for sensing applications, it is widely used a total internal reflection configuration. So here we combine ellipsometry with surface plasmons, and the trick is to combine the spectroscopic ellipsometry with surface plasmons to increase sensitivity. Actually, this configuration also is useful because light, incident light, not directly travels through the ambient, in which we measure some kind of processes. Just only our probe is just only a evanescent wave plasmonic resonance, which is feel the changes of refractive indices of the ambient and changes refractive indices at the metal interface. So in general, ellipsometry measures the amplitude ratio of polarized light and phase difference between them. The phase difference gives, in total internal reflection ellipsometry configuration, gives better sensitivity for absolute values, and it overcomes the traditional commercially available SPR devices where just only intensity, polarized light intensity measurement is used. So as this surface plasma polariton is sensitive to the refractive index changes at the nanometer scale, these resonances being developed as a bio and gas sensors. Surface plasma polariton is real-time, non-destructive and label-free optical method for detection of interaction between various biomolecules, mainly proteins, usually viruses, sometimes cells. I will show you the main principle, how it works. So if we have a prism at which bottom is attached the glass slide with a thin metal layer about 15 nanometers and is placed in the chamber with gas or liquid media or buffer, some kind of buffer solution. And if we have, for example, for biosensing, if we have some kind of molecule, some kind of protein with known concentration, we can inject it into the chamber, and we can monitor how they attach to the surface, to the gold sensor surface. And due to this attachment, due to binding of the molecules to the surface, our plasmonic resonances shifted to the longer wavelength, and through this we can calculate the thickness of the formed layer, the refractive index, and as a result we can evaluate how many molecules we have on the surface, for example. Okay, I will show you some examples of such kind of biosensors, and here will be the comparison between hybrid modes and standard surface plasma resonance. So here we use two proteins, granulocyte colony stimulating factor receptor, which is used for people as a drug for people after chemotherapy. And bovine serum albumin is used more like a model system, like a model protein. So here you can see two structures. One of them is for excitation hybrid modes, TAM plasma polariton with surface plasma polariton, and the standard, which is used in the commercially available SPR devices, where a single SPR is generated. So the main advantage of hybrid modes that the dispersion of hybrid modes can be controllable. So here you can see how it looks here, surface plasma resonance, and here in the right side, this is the single surface plasma resonance. In this part, at the same angles, we have here we have in hybrid mode we have very narrow line which indicate lower losses, which implies that we will have better sensitivity of the sensor. So here we're starting from the granulocyte colony stimulating factor receptor, which is injected in the chamber with known concentration, and this is the curves, resonance curves for single SPR. And you can see here the shift of about 12 nanometers to the longer wavelength, which gives about 8 degrees of ellipsometric parameter psi, and the delta parameter was changed of about 150 degrees. And here you can see the relative sensitivity to the 1 nanometer. So the same was performed with the hybrid modes, and the shift was about 6 nanometers. However, relative sensitivity, the better relative sensitivity was achieved just only for psi parameter here, but for delta, the relative sensitivity was better for single resonance actually. So the next experiment was again with a single and hybrid mode, but hybrid mode was optimized. They choose appropriate angle in order to give a better sensitivity. So here you can see the single SPP due to attachment of, due to binding of bovine serum albumin molecules to the sensor surface, and the shift was about 6 nanometers. And about 4 degrees in changes in ellipsometric parameter psi, and about 50 degrees in delta. So the relative sensitivities was not very high actually. And for hybrid optimized mode, you can see here that both actually both relative sensitivities was better than for single one. And what is important that the delta parameter was much better, which gives actually absolutely better sensitivity than ellipsometric parameter psi or just only intensity measurement of polarized light. And our latest work with the studies of the coronavirus. Here you can see a standard SPR chip, which was attached to the prism and placed to the chamber again. and total internal reflection ellipsometry was used. And I will show you animation how the antigen of coronavirus was attached to a sensor surface. Okay, so this is the antigen of coronavirus, and it was measured in time, the kinetic measurement, and after that, the specific antigen against coronavirus was attached to the, specifically attached to the antigen of coronavirus. So from this measurement, we can evaluate the affinity and dissociation constants between these two proteins, which is actually direct biochemical information, which is further used, for example, for vaccine development, for development of drugs against coronavirus, or for rapid test development. Okay, so in conclusion for that part, it was found that sensitivity of the hybrid plasmonic mode can be controllable by using the strong coupling effect between components, reduces the metal losses of a surface plasmon component in the hybrid plasmonic modes, narrows the plasmonic resonances, and the employing the TAM plasmon polarity resonance as an indirect probe in some cases can provide additional information which is useful for the analysis of adsorption process at the interface. Okay, so the next part is related to the plasmon-based lasers. So the plasmon-based lasers, in other words, is a surface plasmon amplified stimulated emission radiation with analogy with a laser. So it's analogous to the conventional laser, but in a spacer, photons are replaced by surface plasmons or local or sometimes localized plasma, and the resonant cavity is replaced by a nanoparticle or interface, which supports the plasmonic modes. So when gain materials are pumped into excited state, instead of the emitting light, they can transfer energy non-radiatively to the resonant surface plasma. And stimulated emission generates coherent surface plasmons, and energy accumulated in the plasmon oscillation can emit into free space, resulting in a lasing. So conventional lasers based on Fabry-Perot cavities are limited in device size due to diffraction limited, because all photonic modes is limited in size due to diffraction limit. In contrast, plasma nanolasers can overcome the diffraction limit of light and incorporate unique structural design to engineer cavity geometries and optical band structures. So in general, plasmons can overcome the diffraction limit because it's a near field at the optical frequencies. So due to that, we can produce nanometric structures which can radiate rather long wavelength in comparison with their dimensions. So very promising structures for lasing is a array of nanoparticles. So when nanoparticles are arranged by an appropriate period, the scattered light field is in phase with local plasma resonance to the nearby nanoparticle, thus enhancing the plasmonic excitation in the neighbor particle. So this leads to a significant narrowing of plasmonic resonance due to compensation of damping. And here in the picture D, you can see directional lasing from spacer nanoparticle array, and this is the power-dependent. You can see the power-dependent lasing emission. So in general, if we need to produce such kind of structures, Usually it used lithography. It's very reliable and good method. However, it's still rather expensive, and the larger areas is expensive and a little bit maybe time consumption. But we can produce very ordered structures with different periods, and you can see here the plasmonic resonance is actually very good quality with very narrow resonances. And such kind of structures, of course, is mainly used for arrays of nanoparticles to produce. In our laboratory, we're starting to apply direct laser writing to produce similar arrays of nanoparticles. And here you can see the array of micro bumps, nano bumps, actually, with a period of about 600-700 nanometers, which is produced on a thin gold layer. And this is a cost-effective technology, and we can produce rather large areas, up to centimeters. And which is important, that we can obtain the same quality of plasmonic resonances, which implies that these structures can be employed for lasing, for laser-based, for plasmon-based laser. And here you can see the dispersion line of these plasmonic resonances. So in general, of course, structures is not so ordered like we've produced with lithography, and we still cannot obtain such a small period like with lithography. But I hope that in near future we can obtain periods, twice shorter periods, about 300-400 nanometers, which is allowed to use it in the optical frequencies. So okay, so general consideration to integrate nanolasers with on-chip application is efficient device output power on the milliwatt scale, electrical pumping for optoelectronic devices, for optoelectronic interconnections and devices, high modulation speeds for signal processing. So all these properties are obtained in plasmon-based nanolasers. Of course, short device lifetime is a key issue. For example, gain material degradation of laser dye as a gain material. So one more advantage of such kind of nanolasers, that actually the threshold of generation of coherent emission is rather low, and it means that they have low energy consumption in comparison with the traditional lasers. Of course, the goals slightly different and mostly related to the integration into electrical circuits or optoelectronic devices. But in general, surface plasmons are the most collective material oscillation known in nature, which implies they are the most harmonic. And if they are the most harmonic, the coherent emission actually is possible, and it was demonstrated. So a lot of growing number of publication the last decade shows a lot of attention to this field, and I hope in near future, we will have technology to produce reliable and integrated nanometric coherent emission devices. So this is our collaborators, which more or less is involved, and I want to thank for them. Of course, people from our laboratory, which is working in biosensing and in production structures and lasing. Also, other people from our center, which is more or less involved in these studies. So thank you for attention.
Thank you very much, Professor. And now we have one question from the YouTube platform.
Okay.
Probably partly it is answered, but I will ask you once more, and maybe you will expand your presentation according to that question. And so the presentation covered very detailed applications. Can you tell us of examples of well-known technologies where photonic-based nanolasers are or could be applied in a broader sense?
In general, this is integration into electrical circuits and optoelectronic devices, where we can have, how to say, very fast switching up to, at the moment, I think it was reported that we can obtain switching up to 5 femtoseconds. So in such kind of lasers. So in general, now it is related with integration to the electrical circuits, where we can use optical signals which will be transferred into electrical signal. So it will be the main part, I think, now. Of course, in some cases, it is such kind of structures is useful also in sensing application, because they are sensitive to the refractive index changes of the ambient. But the main things, of course, it is integration into optoelectronic and electrical circuit devices.
Okay, thank you very much for your presentation once again, and good luck.
Thank you.
And now it's time for our second presentation, which will be presented by Mr. Tommy J. Lindros, a senior scientist at VTT, Technical Research Center of Finland. And today he will talk about decarbonization and electrification in Baltic countries and Northern Europe. And Mr. Tommy has over 15 years of scientific experience in energy system modeling, support for decision making, and in the energy sector, renewable energies, and district heating and cooling. And I looking forward to his presentation with great interest. So please, Tommy, the upcoming 30 minutes is yours.
Thank you. So it's an honor to speak here, present about the things we study. So in general, it's about the energy climate policies. So it's a bit similar to a presentation at the morning session about the climate change impact, but we instead study more about mitigation. So not that what the climate change would do to our environment, but how we could stop it or reduce the impacts. So, and currently the main measures, in a way, they're the decarbonization, so reducing emissions, reducing the use of fossil fuels, and so far, one of the main measures is the electrification. That's one thing that can be done, but that's the focus of this presentation, and I'll tell soon why. And another limitation or specification we chose in this one is that we present project results from the Baltic countries and Northern Europe. So we do model the European level stuff and global projects, but this focus is on the Baltic countries and Northern Europe. For some reason that stopped my screen sharing. Let's try this. No. It helps if you start from the first slide. Now, so the Paris Agreement sets the framework for all of this. And that's a big international agreement where most of the countries of the world agreed to hold the increase of global average temperature to well below above pre-industrial levels. And to achieve a balance between anthropogenic emissions by sources and removals. For example, forests remove emissions from the atmosphere. So we should first reduce emissions and then go to negative emissions or balance the emissions and sinks. But these objectives, they require major and rapid actions to reduce greenhouse gas emissions all over the world. And Nordic and Baltic countries have committed to be carbon neutral as part of the European Union by 2050, so only 30 years from now. And some countries have even much earlier target years. And the main thing is that there's a great need for enhanced policy action. So to achieve these ambitious goals, and we need a lot of additional measures and a lot of new decisions and technologies to invested and researched. And we also need enhanced policies to realize the opportunities and avoid the risks that the societies will face. You heard of these earlier this morning, and that's an important policy action field, that we both mitigate the climate change and also avoid the negative effects and impacts resulting from the remaining climate change. But this is a background figure, quite general background figure. So it shows that from which sectors, economical sectors, the EU greenhouse gas emissions arise from. And transport is the main source, or was the main source of emissions in 2018. That corresponded roughly 40% of the total greenhouse gas emissions at the EU. And that was followed by power, so production of electricity, and industry, both 20% roughly. And the remaining comes from buildings and other sectors. And 5% of total emissions are mitigated by, or kind of counterbalanced with the forest sinks. So, and when we look the Nordic and Baltic region, the figure is similar, but there are some differences. So the transport is 40%, whereas power and heat is 15%. And for this region, we speak about power and heat because all the countries have quite large share of district heating. So that's centralized production of heating and delivering to buildings. The industry's share is higher. The countries have quite large share of the industry. And because of district heating, the emissions from buildings is much smaller than in EU in average. And the other sectors, that's mainly agriculture and waste management. But the Nordic and Baltic countries have a large area when measured by person and larger agriculture sector, but also larger forests that counterbalance roughly 20% of the emissions in this region. And when you look at the development of these emissions, so the transport sector emissions have been increasing and the other emissions have been decreasing. And the power and heat emissions, they've already reduced almost 50%, whereas the industry has been roughly stable. And we will look at these three sectors in a more increased detail soon. But first, so here are the few main messages, what we find in every study we do, that the carbon neutrality or climate neutrality, as some countries say, that requires rapid decarbonization of power and heat. So those sectors first need to reduce their own emissions and then supply fossil-free energy to other sectors and possibly other regions. For example, the Nordic countries are exporting electricity both to Central Europe and also the Baltic region at the moment. But in future, it could be that both Baltic and Nordic regions could become electricity exporters to Central Europe that has less renewable power resources than what we do have. And that should be followed by emission reductions in cars and buildings. And third, after these, in parallel with these, we should start developing and demonstrating technologies and processes to reduce emissions in industry and heavy transport. These are very difficult and technologies do not exist yet at commercial scale. We do have pilots and some demonstrations for certain sectors, but there's huge amount of work to be done and actual research and also commercial demonstrating, so engineering work. And the last major point is that we also, while reducing the emissions, we need to enhance forest sinks and develop negative emission technologies. So a technology that can take carbon dioxide out from the atmosphere, as the last 10 to 15% of the emissions can be very hard or expensive to mitigate. So it's better just to offset those with forest sinks or the negative emission technologies. But if we look at the power sector in detail, so the falling costs of renewable power are changing the whole energy system at the moment. And the change has been fast and dramatic. And this figure from the IRENA, the International Renewable Energy Agency, demonstrates very clearly that what has been going on in the last 10 years. So when you look at the figure, there's that wide gray bar or a range that shows the cost of the fossil fuel power generation from the existing plant. So that's the cost of running existing power plants. It's in dollars, but that's roughly $50 or 50 euros per megawatt hour, up to 170 euros or dollars per megawatt hour, depending on unit. And you see that price range depending on hour per year. At the Nordic and Baltic region, we have lower electricity price than at the EU, also some Central European countries. But the price of the renewables, especially the solar and the onshore wind power, they have been dropping so dramatically and so quickly that, for example, the solar photovoltaic production cost, that's impossible to extrapolate. So it's really hard to predict how the price will behave for the next 5-10 years, but it will decrease from there. And we are approaching a situation where a new wind power or new solar photovoltaic plant, depending on the region. So the new plant is cheaper than using the existing old thermal unit. And that really starts to change things. And the main questions are that what are the impacts of this? And what's the value of wind and solar production? As the production often happens, well, like when you have good windy conditions, the electricity price may decrease. And when there's less wind or nights, the electricity price might increase. So what's the value and how the system does work? And we do study this in quite many projects. And here's a figure from one of those. So that shows kind of our modeled electricity area. So when I spoke about the Baltic countries and the Northern Europe, so that's a figure from one study where we did model the electricity at the Nordic market region. And we did approximate the Central Europe and some Baltic countries to increase the model calculation time. But we do run the simulations and modeling also with full details from each country. But the bar figures on right, they show the electricity generation in that region at year 2017 and a baseline projection to 2030. And you can see that the amount of wind is likely to more than double, same as with the solar. But as these are northern countries, the solar is not that cost competitive here, but the story is wholly different to Southern Europe. And every other generation, so hydropower and biomass, they remain roughly the same or would remain roughly the same. But the amount of coal drops quickly. And since that study, we did the modeling maybe a year back. So there's been more and more coal bans announced. And the share of coal might fall actually faster than what is shown here. The share of gas might decrease a little or remain the same, and same goes with the nuclear, as that's mostly a political decision. But existing hydropower, that's extremely important block in this figure, as that provides grid balancing and stability. With this amount of wind and solar, the Northern European region is quite lucky that we have so huge amount of reservoir hydropower that we can balance the seasonal and hourly variability of these renewable energy sources by just adjusting the hydropower production. But also the increasing transmission capacity between the countries and within the countries is essential. And that we see in every modeling, that we need increased transmission capacity and balancing from hydropower. This problem would be much more difficult if you have an isolated region, for example, some island country that does not have hydropower. But when we speak about indirect impacts, it gets much more complicated and much more interesting. So when I said that there might be lower electricity prices in the future, that's because the wind power has lower levelized cost of electricity than existing thermal generation. That's the figure I showed from the IRENA. That means so falling average prices, but the lower profitability of the existing generation results to retiring capacity that again increases the electricity prices and loses some inertia in the system, so the balancing power. And it also does change the district heating generation, because Nordic and Baltic countries have a lot of combined heat and power units that produce both electricity and district heating. But these units are losing their profitability due to lowering electricity prices. And then the district heating needs to be generated with either these units with less profit or then with different kind of units that produce only the heat. But the low wind hours also, they are likely to lead to increased hourly prices, thus higher variability of the hourly prices. But when we speak about electricity prices, it's always important to remember that the distribution costs and taxes and other fees are often the most significant cost component for consumers. But for industry and electricity producers, they follow more the market price. And we've done several studies about the regional and sectoral integration. As the sectoral integration can provide a significant amount of flexibility in the system. So when the electricity becomes cheaper, a lot of new users appear, and that might increase the consumption. In some scenarios, actually the electricity generation might increase more than 100% if we assume a very high share of electrification, so a lot of electric vehicles, a lot of heat pumps, and also exporting electricity to Central Europe. And that is a huge change. And main concerns are that wind power planning can be very slow, or the public acceptance might be negative, so it might be hard to build up such many new wind turbines. But to study all the changes and the integrations in the system, we are building a new model that could handle this at regional and sectoral level. So we would build a model with hourly modeling of the power and heat units, district heating grids, electricity grids, also the natural gas network, and combine that with the models of buildings, industries, transport modeling, and to capture all the effects and impacts of the sectoral integration. We need to have all these subsectors within one model that works at hourly or even more detailed level. And we will publish this one as an open source by the end of the year or during the next year, depending how the project goes. But you can afterwards check these links and learn more about this. And similar, little bit deeper dive to transport sector and electric vehicles. Electric vehicles will have lower lifetime costs than combustion engine vehicles in 2020s, so within 10 years. That's a bit bold claim at the moment, but that's how things really seem to develop. So here's results from another of our studies that's still unpublished. It will be published September this year. But the costs of electric vehicles are falling very fast, and new models are appearing every year. The car ranges and charging infrastructure are getting better. And many countries are planning increased taxes or bans on fossil fuel vehicles, or even implementing road tolls or additional parking fees or for fossil vehicles, or freeing electric vehicles from these. But all these changes together, they are making the electric vehicles more cheap and more appealing to consumers. And the figure on right that compares the diesel, gasoline, natural gas, electric fuel cell vehicles, passenger cars on 2020 and 2030. It's a generalization of all different ranges of models available. So that's kind of an average car, maybe lower cost than the average car. But I circled the battery electric vehicles and plug-in hybrid vehicles in that figure. And as you can see, in 2020, the lifetime costs are quite much higher than with the gasoline or diesel vehicle. But when we go to 2030, the gasoline and diesel vehicle costs, they would decrease, but not that much, whereas the battery electric vehicles and plug-in hybrid vehicles would see a cost decrease of almost 30% and becoming much cheaper over lifetime than the traditional combustion engine vehicles. And we already start to see this at a European level. So I collected numbers from the 2020 new registrations at the European level. There's a cool link that you can check. There's a lot of data about this stuff, and I just picked up the main results. But when we look about the fuel types of new cars at the whole EU, so the 11% were battery electric vehicles in 2020, and another 11% were hybrid vehicles. When we look buses, 6% were electric and 10% were hybrid. And when we go to goods transporting, so in vans, the electric share was only 2%. And in trucks, I was actually quite surprised that there was almost 0.5% of electric trucks. I didn't know that before checking these numbers. But in our modeling, we do see electric trucks maybe in 2030s, 2040s, but trucks might go also for the bioliquids, biodiesel, or even natural gas, depending what you assume. But this was a kind of new hint that the electric trucks could appear on a broader markets a bit earlier than what we have previously modeled or assumed. But when we speak about the electrification and alternative fuels, the main findings are that the electrification of passenger transport needs, that would be the first one, and we need new fossil-free electricity for that. So if you run the car with coal electricity, that's not good. But if you invest to both the electric vehicles and fossil-free electricity generation. Then you get the emission reductions on both sectors. And then we need to develop, as I said earlier, we need to develop new low carbon solutions for heavy transport. So trucks, ships, and aviation. Those might be very hard to electrify, especially over long distances, and they might need some other solutions that are not developed at commercial scale yet. We also should aim to produce forest-based biofuels if the carbon stock impacts are sufficiently minor. So in the beginning, I showed sectoral emission figures. So I forgot to mention it there, but both at the EU and at the Northern Europe, the amount of forest sinks have actually reduced a bit. Not much, but when we replace fossil fuels with biomass and biofuels, there is a risk that we do lose part of the forest sinks. And then it's much less efficient emission reductions on the energy sector if that causes forest sink losses of forest sinks. But back to transport. So when speaking about transport, it's always about the global perspective. So the Nordic and Baltic regions cannot develop the transport infrastructure separately from the rest of the EU. So if somebody in Baltic countries would like to drive to Central Europe for holidays, you need a car that works with that transport infrastructure and vice versa. So the Central Europeans should be able to drive to Baltic and Nordic countries with their cars. And similarly, as the car manufacturers are big global players, so it's unlikely that the EU can develop transport infrastructure separately from rest of the world, but that also goes the other way around. So if car manufacturers need to produce EVs for Europe, other regions would likely follow. And we actually saw a similar development already in wind and solar, where Europe went first with those. And then when the costs decreased, the rest of the world started to follow. And now we start to see the big change, but likely something similar will happen in the transport sector. And when speaking about the charging infrastructure, that is a big thing from a user perspective. So detached houses already have options for charging, but city centers will require a lot of special attention and likely some new solutions. And if we get a smart charging things, we can provide flexibility and balancing to the variable generation. So if the car is plugged into charger for whole night, the system could decide automatically when to charge the car and not to burden the system, but balance the variability. And it's likely that the distribution grids would need reinforcing if the power generation from the combined heat and power units in cities decrease and the demand within cities increase. So the cities would need to import more electricity from the system. And I have a quick view on the heat pumps, as new generation heat pumps are much more efficient and can provide higher temperatures than the previous generation. And this is an upcoming change that is collecting speed and force in some pre-runner countries. So the new generation heat pumps can produce district heating. They can produce low and medium temperature industrial heats and still the building heating, but with decreased costs. And the improved efficiencies, the new generation heat pumps can provide improved efficiencies over larger temperature lifts. So for example, a 80-degree district heating can nowadays be produced from air. So you have an ambient air source heat pump that produces 80 degrees district heating with relatively small costs. And if you have a warmer excess heat, the new generation heat pumps can produce industrial heats up to 120, 130 degrees. And this is potentially a very significant efficiency improvement. Here's a map of the Baltic countries where the blue dots show excess heat sources and the pink areas show the district heating regions. And a lot of heat sources are relatively close to district heating. systems. And if we can connect and mix these, we can utilize the unused excess heat. But currently the Baltic countries have some limitations in their policies and pricing. So the large heat pumps need to pay quite large distribution fees and costs. And there's likely a need to revise tariffs and fees to support this more efficient system. The last thing is about the industry. It has large point sources with unique processes. We cannot go through industry with this kind of a simplified manner. Here's a map of a Nordic CO2 mountains, as we have called those. It's a map of a Nordic GIS-based map on the Nordic CO2 emission sources. It shows cities where the emissions is from the heating and transport within the cities. And then it shows the largest point sources from 6 industrial fields. And when we speak any large scale heavy industry, we often end up speaking of individual plants or units. So if we, for example, speak iron and steel industry in Sweden, they have 2 units. So it really goes to very process and company specific. And the topic is much harder, and we often do not have existing solutions, though the share of emissions from these sectors is quite high. And as a summary, I just bring back this slide. And these are the 4 main actions that we do need and should follow in the coming decades. And then when learning more, maybe update these. But that's the current view that what should be done. And thanks. That's what we study in a quick go.
Thank you very much, Mr. Tommy. And I would like to ask from myself, could you come back for the 3rd slide or something else?
Yes, unless, oh, sorry, I stopped. Share.
About the greenhouse gas emission in UA.
Yes.
Yes. And maybe you know what happened in around 2018, that the emissions from industry rapidly decreased.
Yes, so this is the 2008 financial crisis, which was quite heavy, hard times in Europe. That was the Greece crisis and all the related stuff. And you see the recessions in this kind of a greenhouse gas graphs. And now, if we would have the data from 2020, there would be something similar. And then it's about the policies, that how well the sectors recover from such drops.
So in some cases, crises are very good for our environment.
Yeah, but you would need to merge this figure,
yes,
not look only the emissions, but also the value added by the sector. Because it either can be that the industry became more efficient, or then it can be because some industries needed to quit.
Thank you. And we have one question from the YouTube. What is your opinion about CO2 offsetting by establishing new forests? Maybe it is more effective way to reduce emissions.
Yeah, that is a good question. So I kind of rushed through this slide. So especially in the Nordic and Baltic countries, you can see the importance of forests as a offsetter of emissions. So they do currently offset roughly 20% of emissions. But historically, the level has been a bit higher in 2000s. And if the forest sinks keeps decreasing, we need to do a lot more on the energy consumption side. But if we can turn this forest sinks to growing, and then we need to do a lot less in the energy sectors. And that should be much cheaper than the hard emission reductions in industry and heavy transport.
So thank you very much for your really interesting presentation, and best of luck in your future research.
Thank you.
So let's go ahead through our schedule, and the next presentation will be hosted by Dr. Roman Antipenko, a deputy head of the Allegra Laser Development Group at LE Beamlines. His research interests include high energy, ultra short pulse application, dispersion control, and laser-driven particle acceleration. So welcome, Roman. The floor is yours.
Hello, thank you very much for the introduction. Just a sound check, if you can hear me well. Could you confirm that, Vytautas?
Yes, of course, everything is perfect.
Super, cool. So I'll share my screen. Just a second. There we go. So now I assume you can see my slides as well, right? So my talk was initially called Advanced Laser Systems at Eli Beamlines facility. But since I realized that the audience here at this conference is much broader, I expanded a bit the talk into Eli a bit more general as well. So to give you an outline, I divided my talk into four pieces. First is the introduction. What is Eli in general? Then I'll cover very shortly the three facilities, the main Eli facilities which are currently operating. And then I'll focus on the lasers at Eli Beamlines facility in Czech Republic. And if there is enough time, I'll very briefly cover the secondary sources which are driven by these lasers. So the first part is question, what is Eli, right? So the story is begins in 2005-2006, where initial proposal was given to European Union to actually enable European high energy unique facility built in the European Union. So the initiator of the proposal was Jérôme Roux, who got eventually Nobel Prize in 2018 for the CPA technique. And then it was agreed by European Union, and the preparatory phase started, which lasted until 2010, where all the main grounds for how these facility, or in this case facilities, multiple, will be built and managed. So this was the very beginning, and then since 2011, the implementation of this Eli project started. It was agreed that there will be 3 facilities, one in Czech Republic, then in Hungary, and then in Romania. And initially, the consortium was driven basically by these 3 countries plus managing board. And then in 2013, as the organization was evolving, Eli DC, Eli Delivery Consortium, was formed, which included not only the 3 host member countries, which actually had the facilities there, but also included facilities from different countries which already have experience for operating for users and actually managing user campaigns. So this expanded the expertise of Eli and actually made it more like user driven. And then very recently, in May 6th, so it's less than 3 weeks ago, there was Eli ERIC established. So ERIC is a legal entity in European Union law. It is European Research Infrastructure Consortium, and there are already 21 ERICs were found in European Union before that. So ELI ERIC is the 22nd one. And this consortium now is being not on the facility levels, but on the member states levels. So basically, countries as such are participating in this how to say ELI consortium. So the consortium consists of 4 founding members. So it's Czech Republic, Hungary, Italy, and Lithuania. And there are 2 more, let's say, founding observers, 2 more countries, Germany and Bulgaria, who are sort of participating in this, but with let's say, lower rights, but of course, lower responsibilities, and they're considering to join at later stages. So this is the background, let's say, of ELI. And now going to the facilities themselves. So as I mentioned, in 2011, the construction of 3 big laser facilities started. And you can see these are actually already built facilities, how they look nowadays. In the top right corner is the one I'm working in. It's ELI beamlines in Czech Republic. On the bottom left, it is Romanian ELI nuclear physics, ELI NP. And in the bottom right, you can see, I'll just make a pointer here, just a second, here you go. So you can see this is Hungarian ELI Alps, ELI at a second. So to give you the more insight of what is ELI beamlines. ELI beamlines in Czech Republic is located right next to Prague, basically less than a few kilometers from the city limit. It's as you can see, the nice picture is just the tip of the iceberg. The actual facility is much larger. And it hosts 4 lasers, which are, let's say, main drivers for the user experiments, plus some commercially available smaller scale lasers for other experiments. So I'll focus on these laser technology in my presentation in the 3rd part. So to give you the scope of the research that ELI beamlines, the Czech Republic facility, focuses on is mainly high harmonic generation and plasma X-ray sources, and also then Betatron and Compton radiation, laser-driven X-ray, free electron lasers, particle acceleration, and then also exotic high energy density physics, ultra high intensity laser matter interaction, and even astrophysics. So these lasers should enable these experiments, and I'll cover very shortly them. So first of all is the home-built one, let's say, laser system, which should reach more than 5 terawatt peak power. The pulse energy currently achievable is more than 50 millijoules, and we plan to upgrade to 70 millijoules this year, and then hopefully to 100 millijoules in the next couple of years. The pulse duration is 15 femtoseconds, the repetition rate is 1 kilohertz, central wavelength is around 800 nanometers, and the beam profile is close to Gaussian, so it doesn't require imaging along the propagation. The second laser is currently under construction. It has the pump laser was demonstrated to be operational, but now we've changed a bit the pathway, and we decided we would go into the upgrade, and it should have more than 100 terawatts at the output, more than 2.5 joules at 25 femtoseconds. Will operate at 20 hertz with option to go up to 50 hertz. And again, it's around 800 nanometer central wavelength. The third laser is already a petawatt laser. It is 1 petawatt, 30 joule, 30 femtosecond laser, which should operate at 10 hertz and at 800 nanometers. It is titanium sapphire based laser. And the fourth one is the most, let's say, powerful one. It should give us 10 petawatts, 1.5 kilojoules at 150 femtoseconds at 1 shot a minute. So these are the main lasers that are planned to be in Dolny Břežany, Czech Republic. So Dolny Břežany, just to let you know, this is a small, let's say, town right next to Prague. So the second facility of ELI consortium is located in Szeged in Hungary. And the main research focus there is much shorter pulses, like attosecond pulses in XUV, coherent X-ray beams. So it requires CP stabilization, and they also think of charged particle acceleration experiments. So they have more lasers, and they plan to expand even further to keep adding beam lines. So HR1 and HR2 beam lines, they are provided by active fiber lasers and are based on parallel amplification in fiber rod lasers, and then coherent combining afterwards. And they're similar in parameters. The difference is the energy available per pulse. So it's up to 0.8 terawatt beam line with 6 femtosecond pulse duration due to post compression, operating at 100 kilohertz. So you can see this is huge average power, and with CP stabilization, and the central wavelength is around 1030 nanometers. Another system is Silos 2A. It has been delivered by a consortium of light conversion and XPLA companies. It's operational and provides more than 4 terawatts of peak power at 30 milljoules, sub 10 femtoseconds, around below 8, basically, 1 kilohertz, CP stabilized, perfect energy stability, and it operates in 800 something nanometer central wavelength. SEA laser, or C, is basically a small brother of Silas. It's Silas experimental alignment laser, so it's delivered by XPLA, and it's a bit downgraded Silas version, which operates at 10 hertz. And then there is also mid-IR beamline, which was delivered by Fastlight company, and the main interesting feature of it operates at 3 microns. So it's relatively low energy, but however, high repetition rate, but almost few cycle at this wavelength. And now switching to the next ELI facility, it's a nuclear physics facility in Măgurel, Romania. And their main research, as you can guess from the name, is nuclear physics. So they plan to focus on basically exotic nuclear and photofission, laser gamma beam interactions, but also see if they can do the positron sources and do some radioisotopes for medical applications and so on. So their bet was on a single laser system, which would have 2 outputs. So it's a laser with 2 outputs, each 10 petawatt peak power. So basically each output of the laser is giving more than 240 joules in output, and well compressed to below 24 femtoseconds, it gives you 10 petawatt peak power per pulse. So in this mode, it can operate in 1 shot per minute. However, it can operate in 3 modes, right? So it can be downgraded energy, where it can upgrade the repetition rate. And then you can go even further and increase the repetition rate, but keeping the, let's say, average power the same. And you can go to 100 terawatts, but already at 10 hertz. So this is quite universal laser, which can give you multiple ways of operating and doing different experiments. So that is for the introduction on the ELI facilities. I guess you get some idea what ELI is about. And now I'll switch to actual lasers at ELI beamlines. This is where I work. And here I can give you some more details on the lasers we have. So I'll begin with the cross section of the building. Our building is laboratory laser building, consists of 3 floors. The upper floor is support room, where we have all kind of support technology. Mainly it's cooling systems or capacitor banks for one of the lasers. And this is used for just support technologies. So the ground floor is dedicated for lasers and laser operations. It has 4 halls. So we call them L1, L2, L3, and L4. And they contain 1 laser each. So the first one is L1 Allegra, the 5 terawatt beamline operating at 1 kilohertz. The second one is so-called L2 Dua, and it's supposed to be 100 terawatt up to 50 hertz system. The third one is L3 Happels, 1 petawatt laser, and the fourth one is 10 petawatt. So interesting feature about the lasers is that 3 first ones, L1, L2, and L3, based on dye pumped technology. So these 3 lasers, they're using laser diodes for pumping, while L4 is still using the flash lamp technology. So the idea behind it was that diode pumping should allow much easier thermal management, as well as much longer life of the laser with less maintenance, and as well the energy stability in the end. And the underground floor is experimental halls. So we have chosen the way to deliver the lasers is actually through the ceiling of the experimental halls. So there is a beam transport which delivers the beams into individual halls. And also the interesting feature of ELI is that we could, in principle, use multiple lasers in different halls, because there are switch yards which allow us to use let's say 2 laser beams in one hole and then 2 laser beams in the other hole. So this is quite universal setup. In addition to that, the idea is that lasers can be synchronized to the same facility clock, which means that all shots are timestamped, so you can trace back to the to all the shots to recover the what were the measurements, but also allow experiments where different lasers can shoot the same target with some delay, and this is quite some interesting physics happening there. So I will begin in more detail with L1 Allegra laser. This is actually the laser I spent most of the time on, and this is the laser I was hired basically to work on initially in 2013. The laser it is based on the thin disk laser technology and OPCPA. So the thin disk lasers are being used as pumps, and OPCPA is the broadband pulse amplification, which is then being compressed to below 20 femtoseconds. So this is how it looks in the facility. We have one Allegro Rezo on top, and then we send the beam down, and there is experimental hall where we have high harmonic station or X-ray source hatch or some other experiments happening. So to give you more detail on this laser, it's as I mentioned, it consists of thin disk amplifiers. In our case, there are 5 of them. At the heart of the system, there is a titanium sapphire oscillator, which actually provides both 1030 seed for the pump lasers and broadband signal for amplification in the PCPA. So this means that the pump and signal for PCPA are already optically synchronized. However, of course, due to thermal drifts and some noise, additional feedback loops are needed to ensure much better synchronization. The reason we need that better synchronization is because we stretch the pulse only to a few picoseconds, and this allows us to compress the pulse at the end of the amplification entirely with chip mirrors. So there is no propagation through the bulk material, which also ensures the better thermal stability of the laser. If we change the power, it means that the beam quality doesn't change much. So the whole laser is based on basically 7 OPCPA stages, pumped by 5 lasers. So these 2 lasers are home built, and these were provided by Trum Scientific, and I'll go in details in the next slides. And currently we are operating this laser at up to 55 millijoules at 1 kilohertz. So to give you more detail, this is how the front end looks and how it operates. We have up to 11 millijoules output. This is how all thing is in air. It's 4 stages. First 3 stages are pumped by a regenerative amplifier with a single head with 30 millijoule output and around 16, 17 millijoule in a second harmonic. The compressors are MLD grating compressors. And the spectrum you can see is quite broad, and it allows sub 15 femtosecond compression. And the beamline itself, as I mentioned, is technology, let's say, split. Part of it was delivered by Trum Scientific Lasers. We have 230 millijoule energy regenerative thin disk amplifiers, which are then compressed and frequency doubled, and which are pumping the OPA. So this portion, the compression and the OPA is done by Eli at home, like this is by our bioscientists, but while lasers were provided by Trum Scientific. So one thing to mention is that compression and amplification and compression of the broadband happens in vacuum, and this has multiple benefits as well as drawbacks, but the benefits are that we have better pointing stability, and we don't have nonlinear effects happening in air because the pulses are still quite short. So we're compressing these pulses to sub 2 picoseconds. So just to summarize, these regenerative amplifiers can provide 230 millijoules at 1 kilohertz, and Eli beamline's portion, and this was done. We did a vacuum compressor with two decks, 3 compressors. It's all in vacuum. And the compressor design actually allows for the upgrade. We can upgrade those amplifiers with extra multipass amplifiers and go up to 1 joule at 1 kilohertz. So this is something really exciting, and we're hoping in the nearest future to see that. And now going for the PCPA section, PCPA is also done in vacuum. It's much more compact because it's just single pass of PCPA. It's 3 stages. We can have quite high gain and efficiency in those stages. So it's like stage 5, stage 6, stage 7 here, you can see. They're all based on the LBO crystals. We are taking care of thermal management. So there are special idler reflectors at around 1.5 micron, which are picking off dispersed idler from this non-collinear parametric amplification, and they're dumping it into a special water-cooled beam dump. And the crystal sizes of the LBOs are around 3 centimeters, 3 by 3, and stage 7, which is already prepared for higher energies, is slightly larger. It's more than 5 by 5 centimeters clear aperture. And the final stage of this laser is the chip mirror compressor. This is our development as well. It consists of 2 modules which can accommodate 20 mirrors each. So the negative GDD chirp mirrors, they have around 180 to 100 femtosecond square negative, and they allow to compress the pulse from 2.5 picoseconds to below 15 femtoseconds, just by bouncing through these mirrors. So the advantage of the chip mirror compressor is not only the thermal management, let's say, and nonlinear effects that could happen in the bulk, for example, but also it also has a high efficiency. It's less than 10% loss. And the fine-tuning of the compression happens using Dazzler. So we have a Dazzler in the front end, where we fine-tune the high-order dispersions, which are not compensated by chip mirror compressors. And this is how it looks with the actual beam. So we have an option of actually having the auxiliary output partially compressed, which is not implemented at the moment. We are sending the full power through into the main compressed beam. But in principle, the design allows us to have an auxiliary beam for this. This is the best compressed pulse we have measured. It's around 14 femtoseconds, and the contrast of the laser is also I would say very good. It's better than 10 to the 9. There is a small artifact, and actually, if you go let's say 5 picoseconds from the main pulse, you can see that the contrast drops even lower. It's basically the measurement limit of the device. This is encoded in the fact that OPCPA itself does not produce, let's say, light outside of the pump pulse, and since we have short pumping, basically, if there is any parametric fluorescence, it is all within few picoseconds from the main pulse. This is how the beam profile looks. It's, let's say, not perfect Gaussian at this point, but close to that. This is 55 millijoules after compression, so it's more than 60 after amplification. 15 femtosecond pulse duration, and more than 3.5 terawatts peak power. So now I'm switching to the second laser we have. So that was all for the kilohertz laser. The second laser, to Duha, is a terawatt system, and it has an interesting feature. In the front end, we decided, it's based on the feedback from the users, that it would be really nice to have mid-IR source as well in ELI beamline. So the front end will provide also the 2 micron, 2 kilohertz auxiliary output. But the main beam is supposed to be 3 joules compressed to 25 femtoseconds at 20 hertz, upgradable to 50 hertz, and at around 820 nanometers central wavelength. The idea behind it is to have the diode pumped Ytterbium YAG nanosecond laser with high energy output, which would be then second frequency doubled and used as a pump for OPCPA. The source for the OPCPA would be supercontinuum preamplified by thin disk pump laser in the front end. So this is how this main amplifier looks like, the Ytterbium YAG, the high energy one. This is before, it's after installation, but way before it's incorporated into actual system. These blue boxes with gray boxes under them are the pump diodes for the head. This is a cryogenic head. It consists of 4 YAG slabs cooled by helium. And this is a closed loop with Brighton cooling engine, which cools down the disks to 150 Kelvin. So the capacity of this Brighton cooling engine actually defines to which pumping energy we can go, how if we can run at 20 hertz or 50 hertz, and that's why the upgrade is currently happening. And the compressor for 25 femtoseconds is currently in construction. It's a huge vacuum chamber. So I cannot tell you more about this at the moment, but it should be operational by 2023. And hopefully then I can show you more interesting results. So this is how this L2 dual laser looks now. So over there is that this main amplifier, which I showed you in the slide before. It's already incorporated into the system. This is the front end, and the laser is gradually taking shape. So now I'm going to switch to the third laser. So the third laser is called L3 HAPLS. It's a high repetition rate advanced petawatt laser system. So it was developed together with Lawrence Livermore National Laboratory and Eli Beamlines. Also our staff was in Livermore helping to actually construct or get trained on how the laser is operating. So it is a 1 petawatt laser system which should operate at 10 hertz. It is based on the TISAF technology. So it is pumped by neodymium YAG pump laser, which is in turn pumped by diode pump laser. Sorry, by laser diodes. And Eli Beamlines developed the compressor, the short pulse compressor for this laser to be able to compress this 1 petawatt, to reach this 1 petawatt to compress 30 joules to below 30 femtoseconds. So this is a block scheme of the laser. It's basically consists of a short pulse front end, where it's also based on the TISAF technology. And then it's 2 large titanium sapphire amplifiers, both pumped by DPSSL pump lasers. So both pump lasers are pumped by diodes, by laser diodes. And then there is a vacuum grating compressor, and then of course we're sending the beam down to the experiments. The interesting feature is that the pump laser of the final, let's say, better, larger TISAF amplifier is helium gas cooled. So it is consists of slabs, which actually here it is. It consists of slabs which are stacked in a way that allows helium gas go around them and cool them efficiently. So the interesting features of this laser is that it's diode pumped still, a petawatt laser which is diode pumped. And we have this helium gas cooling technology for this, and this is how the head looks. And the recently demonstrated results, the compression results are here. So we've compressed 13 joules at 27 femtoseconds, and we've reached more than half a petawatt. And the contrast you can see is also very good. And this is how the output of the laser looks like. This is the compressed beam. The system is automated from the control room, operated by a few people. And this is how the actual system looks like. So now I'm switching to the fourth laser. This is an interesting laser because it is kilojoule CPA laser, which has 10 petawatt peak power. So this is how the main laser looks like, and this is the compressor of the this 10 petawatt compressor. The laser was delivered by National Energetics and Explo Consortium, and it was built in Texas, Austin, and delivered to Prague. So it consists of the pulse conditioning front end, let's say, then 5 OPCPA stages pumped by lasers from Explo, which can be pulse shaped. And then this 4 joule output goes into the power amplifiers, which are flashed and pumped. And this is the first amplifier, and then the second one. This consists of slabs of neodymium glass slabs. And at the output, we get more than 1.5 kilojoules, and it is compressible to below 150 femtosecond, if I'm mistaken. So this is how the laser looks like. So this is the front end, nanosecond OPCPA front end. This is 100 joule first amplifier, and this is 1.5 kilojoule second amplifier. So this is how the beam profile looks like. The compressed pulse, 150 femtoseconds, and the energy is 1.5 kilojoules. It also has an option to operate at slightly above 1 kilojoule at longer pulses. So instead of the broadband pulses, it's being seeded by narrowband pulses. So the compressor for this petawatt laser is a grating compressor. You can see that's why the chamber is so big. It's 15 meter long. And to accommodate the 60 centimeter beam size on the gratings plus the second gratings, we have an interesting feature. It's the phasing of the gratings. So instead of having a large grating, we have a mirror which actually allows to have a virtual image of the grating there. And basically, by having a mirror next to a grating, we're able to compress much larger beam that grating would originally allow. So this is how the chamber of the 10 petawatt compressor looks like. So this is all for the lasers at Eli beamlines, and I very shortly want to show you guys the secondary sources we have. So first of all, before I continue, I wanted to invite you to check out the virtual tour of Eli beamlines, because all we have there only an L1 laser. The others are too proprietary to be on a virtual tour. However, we have all the experimental halls there, and you can really enjoy actually looking inside how the lab looks like with all the technology there and how it works, and there are even some explanations. So regarding the experiments we're doing, it's first of all the particle acceleration, which was done recently with L1 laser. It is laser wake field acceleration experiment, where in the gas jet, the electrons are being accelerated by the laser beam. So these are very fresh results, and we're expecting to reach mega electron volts. So other sources we have is high harmonic beamline. I'll show one slide afterwards explaining how it works a little more in detail. And it can operate in dual mode. One is for the backup laser with just a few millijoules, and for L1, it can also generate much higher photon flux and shorter wavelengths. There is also plasma X-ray source, and for L3 driver for, let's say, petawatt lasers, we have Betatron or Compton scattering sources. So this is the HG beamline in experimental hall 1, driven by L1 laser. It has multiple focusing configurations. It can be focused, the laser can be focused from 2, 5, or 15 meters distance with a spherical mirror. And depending on the energy and the size of the focal spot required, and the expected lambda of wavelength of the XUV pulses is presented here. So this is a short comparison of XUVs demonstrated with L1 laser recently. So we can reach up to 85th harmonic. And this is the plasma X-ray source. Plasma X-ray source is currently under development, and it's planned to use solid density targets there. And the targets would be either copper tape or liquid metal jet or water jet. So this should provide us with X-ray emission, which then can be used for experiments further down. Another beamline we have in experimental holes is driven by petawatt lasers. It's basically for ion accelerator with selection and transport, and then again dosimetry and sample radiation. So this is accelerated proton technology. So here is how it looks. This is the beam transport from the laser interaction chamber where the protons get accelerated, and then this is the experimental station. This is how it looks in real life. And one of the largest chambers for experiments we have is P3 chamber. It should combine L3 and L4 lasers in a single chamber. It should be operational this year, and this is how it's done, let's say. And the interesting feature, maybe I can show it really quickly. Zoom in. You can see how large it is. Basically, the person is standing there, so it is just quite an impressive chamber for experiments. This is a short animation of how it actually looks. Just a reminder, you can go to the virtual tour and have a look the current state of the laboratory. And at this point, I would like to conclude my talk, just to give all the credits for the people who work at Eli. There are plenty of very talented people, and they're all trying hard to actually make Eli happen and to be one of the best facilities in the world. But if you are a talented student, of course, there's always place for more talented people. So if you're planning on joining Eli, please consider applying. And that is all. So thank you very much. And this will conclude my talk.
Thank you very much, Mr. Roman, for your really interesting and interactive presentation, and perfect fit in time. And during this your presentation time, we received one question to you from YouTube. What tasks such powerful lasers as 10 petawatt employed for? Could you name a few practical applications of research done using them that we can relate it to?
So maybe one of the most interesting experiments that can be done with such powerful lasers is, at least for people to relate to, is from this astrophysics experiments. The idea is that with such powerful lasers, you can heat up and compress the matter in a very short time, but to extreme temperatures and extreme densities. So such extreme conditions occur only in the cores of planets or in the stars. So this allows physicists to actually probe the effects or processes that happen in these really extreme conditions. And this is one of the most probably exciting features that can be actually accessed by such powerful lasers. So this would be my answer.
Okay, thank you. And also, please leave that link to the virtual tour, and we'll try to share via our network channels for our all participants.
Do you want me to send it to you?
Please leave only in chat, and
okay.
It will be great. So thanks a lot once more. And our keynote session, little by little, coming to the end. And now we will have last but definitely not least presentation from the Miss Paula Peiro Garcia, and the Executive Coordinator of Horizon 2020 Auroral Project. This presentation will be about smarter communities. The smart community concept is quite new and involving as the number of communities using smart technologies continues to grow. This concept is embedded in the mentioned project, which focuses on increasing connectivity and delivering a digital environment of smart objects, interoperable services platforms able to trigger dynamic rural ecosystems of innovation chains, applications, and services. So respectively, I would like to invite Ms. Paula to tell us more about that. So the digital floor is yours.
Thank you very much. I hope I will share my screen. I hope you can see. Just a moment. Okay, share. Wait. Can you see my screen?
Yes, everything is clear.
Okay, thank you. Well, thank you very much for the invitation today. It's a pleasure to be here in this such a great panel. So thank you, first of all. Well, my presentation today will be very short idea about the project, Auroral project, which we are coordinating. Okay, first of all, yes, it's true that I'm from Spain, but this project is led in Portugal, in Alentejo region. I'm based in Portugal also. So I will show you a bit about the project that started the 1st of January of this year. So Auroral name, the meaning of Auroral acronym is architecture for unified region and open digital ecosystems for smart communities and wider rural areas, large scale application. So this is the meaning of Auroral acronym. So in very brief numbers, we are 25 partners around all Europe from 11 European member states. We have, for the moment, 8 pilot regions that we will open for more, but for now. Then we have more than 5 domains, which are farming, tourism, mobility, energy, health, among others. And the duration of the project is 4 years. As I said, started in January of this year and will be 48 months of duration. Here, just to show you the logos of all the partners that we are. We have entities, local authorities, regional authorities, research centers, universities, business companies. Well, different. We have different knowledge from all Europe to cover all these aspects. So just to show you a bit. Then about the approach of our project Auroral, it's divided. We can divide it from co-development and interoperability and ecosystem and empowerment. Regarding the co-development, Auroral focuses on delivering an interoperable, open and integrated digital platform that will serve for rural region and contribute to an European globally competitive ecosystem of digital services and business to empower smart communities. Regarding the ecosystem, our overall objective is to deliver a dense network of smart communities under a common multi-operability framework. That the objective is to succeeding the just, fair, open, and digital transformation. Our rural pilot regions that I will show in the coming slides implement the concept in all Europe, targeting an investment platform. That investment platform will be developed in the upcoming years of innovative services focused on smart communities into rural areas. Regarding the market orientation, here you can see the map, more visual about the pilot regions and partners where are based in our project. Is demonstrated by cost-efficient and flexible cross-domain applications through large-scale pilots in 8 regions in Europe. So we have one in Portugal, in Alentejo, which is more or less here. Then we have in Spain, in Catalonia, another pilot region. Another we have in Finland. In Norway, we have 2, one in tourism and another health domain, and another one in Sweden. So we have a good balance, let's say, between, and Austria, sorry, I forgot, and Italy, between the different regions in Europe. So Aurora is expected to be a driver of the emergence of a widespread network of smart communities in Europe and to contribute to balance urban and rural opportunities for all Europeans. This part, I think, is really important to go more into, and I will explain more our vision about this balance between urban and rural opportunities, which is the main difference between smart cities and smart communities. Also very, very visual slide to show you about the pilot regions. So we have 5 use cases, which are in one domain, which are Alentejo tourism, in Italy farming, in Norway health, in Sweden energy, and in Finland mobility. Those are the one target domain. And then we have cross-domain, transversal, let's say, that are in Alentejo, in Italy, Norway, in Austria, and Spain. So 3 of them are target domain and cross domain. Regarding the impacts, we have several impacts, I hope. And I just list some of them here. Some of them are more technical, some of them more social aspects, let's say. Regarding the impacts, we will validate the brokerage platforms by an increase of cross-cutting applications and services. We will demonstrate and showcase cross-sectoral platforms and interoperability. We will increase perspectives for future digital industrial platforms by validation of technological choices. We will demonstrate the benefits of data sharing across our platforms from different sectors. We will have significant and measurable contributions to standards. We will explore and validate new industry and innovative business models, validated in the context of our pilots. We will emerge of sustainable ecosystems around digital platforms. We will overcome the digital divide between rural and urban areas, once again, and to develop the potential offered by connectivity and digitalization of rural areas, which is the main point here. Increased number of services and applications operated by European companies, especially small business and entrepreneurs. We will strengthen links with other bottom-up programs and initiatives supported by regional, national, and European policies. We will create opportunities for entrepreneurs, especially for SMEs, promoting the new market openings and providing the access to data sets and to the users, creating new business in the rural areas. We will increase the number of platforms, application, business processes, and innovative business models. And we will improve the quality of life in rural areas, increasing the standard of living and services for citizens. So these are some of the examples of the impacts that, that we want to achieve with our rural project. Regarding the topic of smart communities and being more focused here on this. As I was saying previously, the smart cities programs that all of us, we know, had a bigger impact on the cities. So the difference between rural and urban areas now is bigger. Then in the rural areas, we have the lack of digital infrastructures, also the poverty rate and social exclusion. Then we have also the rural population, which is less. The population now in the rural areas, as you know, a lot of people is moving from rural areas to the cities, so is decreasing. And the pressure in the environmental aspects. So implementing the new programs as Digital Europe Decade, in the smart communities, we will connect and integrate different subsystems, including, as I showed before, energy, transportation, healthcare, agriculture, tourism, education, and among different areas that we are working on to meet the people needs, to check what is needed by the population in the rural areas, with a particular focus on the active integration in the most vulnerable categories to protect the environment and ensure the climate neutrality. So this is the dense network that I was explaining before of smart communities, is what we called Smart Tomorrow Initiative. Here, I want to focus also in the young generation and entrepreneurship. We have the new generation of Europe and the digital decade, and among different programs that were launched by European Commission, and we are taking from them some opportunities, digital opportunities that we will implement in our rural. So digitalization and favorable climate for entrepreneurship in rural and remote areas support the young generation. So with these activities that we will develop, we would like to stay in their communities, the young people, and be able to profit from modern technologies and developments. We will improve the education and digital education outside the metropolitan cities. And we will give more flexibility in terms of work, as you know, with digitalization in the last months, as home office, as internet everywhere, and less commuting. So here I wanted just to show you a bit this aspect that we want to not be so big, the gap between the cities and the rural areas, and to spread this concept about our rural pilot regions. So, well, this was really, really short. Our project, as you can imagine, is have different areas in during these 48 months. So I just wanted to show you a bit of our project, but I invite you, of course, to go to our site and social media and to address to the project coordinator or to me as executive project coordinator for any additional information if you want to know more about our project and what we will do during the upcoming months. So thank you very much.
Thank you, Paula. And as I can see, there are no questions from our listeners, but I have one. Does smart communities have any geographical barriers? Does there are any geographical conditions which will lead to difficulties to implement it?
Difficult barriers in terms of geographical, you mean?
Yes.
Well, for the moment, we just started the 1st of January, and we are now doing the state of the art of each region. For the moment, we will find, of course, some difficulties. We are evaluating that. We are working on that. There are some from our pilot regions. There are some which are smaller and more difficult to have access there than others. But for the moment, we didn't find any.
Okay, thank you very much for your attendance here, and best of luck for your project.
Thank you very much.
So that's all for this day, which was really intensive of knowledge sharing. And I hope that our participants have gained incomparable experience from the listened presentations of our invited keynote speakers. Therefore, I would like to express my additional great thanks for them. And accordingly, I would like to invite active members of the organizing committee to unmute themselves. And let's applause for our keynote speakers. So it was really glad to see all of you in CYSENI 2021. And for the other conference participants, I'm inviting you to be active all this week on CYSENI.com and check topics of your interest, where unique, interesting, creative, and applied in practice scientific researches are presented. Also, please leave comments or questions below the listened presentations, and the answers will be provided within the short time. If you have any difficulties in the connection to the presentations, please contact us via provided email on CYSENI.com website, and we will help you to access them. So finally, I really appreciate all of you participations at the CYSENI 2021 opening. Thank you very much once again, and enjoy watching the presentations from all our participants. Goodbye.